The following is a conversation with Brian Keating, experimental physicist at UCSD and author of Losing the Nobel Prize and Into the Impossible. Plus, he's a host of the amazing podcast of the same name called Into the Impossible. This is the Lex Fridman podcast. To support it, please check out our sponsors in the description. And now, here's my conversation with Brian Keating. As an experimental physicist, what do you think is the most amazing or maybe the coolest measurement device you've ever worked with or humans have ever built? Maybe for now, let's exclude the background imaging of cosmic extragalactic polarization instruments.
Yeah, I'm slightly biased towards that particular instrument, but
Talk about that in a little bit.
Yeah, but certainly the telescope to me is a lever that has literally moved the Earth throughout history.
So the OG telescope?
The OG telescope, yeah. The one invented not by Galileo, as most people think, but by this guy, Hans Lippershey in the Netherlands. And, you know, it was kind of interesting because in the 1600s, 1500s, 1600s, it was the beginning of movable type. And so people, for the first time in history, had a standard by which they could appraise their eyesight. So looking at a printed word now, we just take it for granted, 12-point font, whatever. And that's what the eye charts are based on. They're just fixed height. But back then, there was no way to adjust your eyesight if you didn't have, perfect vision. And there was no way to even tell if you had perfect vision or not until the Gutenberg Bible and movable type. And at that time, people realized, hey, wait, I can't read this. You know, my priest or my friend over here, he can read it, she can read it. I can't read it. What's going on? And that's when, you know, these people in Venice and in the Netherlands saw that they could take this kind of, you know, glass material and hold it up and maybe put another piece of glass material and it would make it clearer. And what was so interesting is that nobody thought to take that exact same device, you know, two lenses and go like, let me go like this and look at that bright thing in the sky over there until Galileo. So Galileo didn't invent it, but he did something kind of amazing. He improved on it by a factor of 10. So he 10x'd it, which is almost as good as going from 0 to 1 as going from, 1 to 10. And when he did that, he really transformed both how we look at the universe and think about it, but also who we are as a species, because we're using tools not to get food faster or to, preserve, our legacy for future generations, but actually to increase the benefit to the human mind.
Somebody mentioned this idea that if humans weren't able to see the stars, maybe there was some kind of makeup of the atmosphere, which for the early humans made it impossible to see the stars, that we would never develop human civilization, or at least raising the question of how important is it to look up to the sky and wonder what's out there, as opposed to, maybe this is an over-romanticized notion, but like looking at the ground, it feels like a little bit too much focused on survival, not being eaten by a bear/lion. If you look up to the stars, you start to wonder, what is my place in the universe? You think that's modern humans romanticizing?
I think it's a little romantic, because they also took they took the same two lenses and they looked inward, right? They looked at bacteria, they looked at, hairs, and in other words, they made the microscope. Yeah. And we're still doing that. And so, to have a telescope it serves a dual purpose. It's not only a way of looking out, it's looking in, but it's also looking back in time. In other words, when you see a microscope, you don't think, oh, I'm seeing this thing as it was, 1 nanosecond ago. Light travels 1 foot per nanosecond. I'm seeing it, no, you don't think about it like that. But when you see something that's happening, on Jupiter, the moon, Andromeda Galaxy, you're seeing things, back when Lucy was walking around the Serengeti Plains. And for that, I think that took then the knowledge of, relativity and time travel and so forth. It took that before we could really say, oh, we really unlocked some cheat codes in the human brain. So I think that might be a little too much, but nevertheless, I mean, what's better than having a time machine? It's like we can look back in time. We see things as they were, not as they are. And that allows us to do many things, including speculate about that. But one of the coolest things, I don't know if you're familiar with, so I'm a radio astronomer. I don't actually look through telescopes very often, except, on rare occasions when I take one out to show the kids. But a radio telescope is even more sort of visceral. I mean, it's much less cool because you look at it and you're like, all right, it looks cool. It's kind of weird shaped thing. Looks like it belongs in sci-fi. It's going to blast, the Death Star or whatever. But when you realize that when you point a radio telescope at a distant object, If that object fills up what's called the beam, which is basically the field of view of a radio telescope, is called its beam. If you fill up the beam and you put a resistor, just a simple absorbing piece of material, at the focus of the radio telescope, that resistor will come to the exact same temperature as the object that's looking at, which is pretty amazing. It means you're actually remotely measuring. You're taking the temperature of Jupiter or whatever in effect. And so it's allowing you to basically teleport. And there's no other science that you can really do that, right? If you're an archaeologist, you can't, let me get into my, my time machine and go back and see what was Lucy really like. It's not possible.
So the same thing happens. This is where I've learned about this from March of the Penguins. When the penguins huddle together, they, the body temperature arrives to the same place. So you're doing this remotely. It's the March of the Penguins, but remote.
And we do it from Antarctica too. So there are some penguins around when we do it.
Okay, excellent. You mentioned time machine. I think in your book, Losing the Nobel Prize, you talk about time machines. So let me ask you the question of take us back in time. What happened at the beginning of our universe?
Okay. Usually people preface this by saying, I have a simple question. So, what happened before the universe began? What happened?
Brian Keating teaching me about comedy. I have a simple question for you. Let's take two. I have a simple question. What happened at the beginning of our universe? There you go.
All right, good. So when we think about what happened, it's more correct, it's more logical, it's more practical to go back in time starting from today. So if you go back 13.874 billion years from today, that's some day, right? I mean, you could translate it into some day, right? So on that day, something happened earlier than the moment exactly now. Let's say we're talking around 1 o'clock. So at some point during that day, the universe started to become a fusion reactor. It started to fuse light elements and isotopes into heavier elements and isotopes of those heavier elements. After that period of time, going forward back closer to today, less, 10 minutes earlier, or later rather, coming towards us today, we know more and more about what the universe was like. And in fact, all the hydrogen, to very good approximation in the water molecules in this bottle, almost all of them were produced during that first 20-minute period. So I would say, the actual fusion and production of the lightest elements on the periodic table occurred in a time period shorter than the TV show, The Big Bang Theory.
Well done, sir.
Most of those light elements, besides hydrogen, aren't really used in your encountered, right? We don't encounter helium that often unless you go to a lot of birthday parties or pilot a blimp. You don't need lithium, hopefully, but other than that, those are the kind of things that were produced during that moment. The question became, how did the heavier things like iron, carbon, nickel, we can get to that later. And I brought some samples for us to discuss and how those came from a very different type of process called a different type of fusion reactor, and a different type of process explosion as well called a supernova. However, if you go back to beyond those first 3 minutes, we really have to say almost nothing because we are not capable, in other words, going backwards from the first 3 minutes, as famous Steven Weinberg titled his book, we actually marks a point where ignorance takes over. In other words, we can't speculate on what happened 3 minutes before the preponderance of hydrogen was formed in our universe. We just don't know enough about that epoch. There are many people, most practicing card-carrying cosmologists believe the universe began in what's called a singularity. And we can certainly talk about that. However, singularity is so far removed from anything we can ever hope to prove, hope to confront, or hope to observe with evidence. And really only occurs in two instantiations, the Big Bang and the core of a black hole, neither of which is observable. And so for that reason, there are now flourishing alternatives that say you can actually, for the first time, ask the question that day, Tuesday, in the first moments of our universe, there was a Tuesday a week before that, 24 hours times 7 days before that. That has a perfectly well understood meaning in models of cosmology promoted by some of the more eminent of cosmologists working today. When I was in grad school over 25 years ago, no one really considered anything besides that Big Bang, that there was a singularity. And people would have to say, as I said, we just don't know. But they would say some future incarnation of some experiment will tell us the answer. But now there are people that are saying there is an alternative to the Big Bang. And it's not really fringe science as it once was 50, 80 years ago when these models, by the way, the first cosmology in history was not a singular universe. The first cosmology in history goes back to Akhenaten, Ra, and the temples of Egypt in the 3rd millennium BC. And in that, they talked about cyclical universes. So I always joke, that guy, Akhenaten's court, he'd have a pretty high H index right about now, because people have been using that cyclical model from Penrose to Paul Steinhardt, Anna Aegis, and right up until this very moment.
Can you maybe explore the possible alternatives to the Big Bang theory?
So there are many alternatives, starting with the singularity, quantum cosmologically demanding singular origin of the universe. That stands in contrast to these other models in which time does not have a beginning. And many of them feature cycles, at least one cycle, possibly infinite number of cycles, called by Sir Roger Penrose. And they all have things in common, these alternatives, as does the dominant paradigm of cosmogenesis, which is inflation. Inflation is can be thought of as this spark that ignites the hot Big Bang that I said we understood. So it's an earlier condition, but it's still not an initial condition. In physics, imagine I show you a grandfather clock or a pendulum swinging back and forth. You look away for a second, you come into the room, pendulum swinging back and forth. Alex, tell me, where did it start? How many cycles is it going to make before you can't answer that question without knowing the initial conditions. In a very simple system, like a one-dimensional simple harmonic oscillator, like a pendulum. Think about understanding the whole universe without understanding the initial conditions. It's a tremendous lacuna, a gap that we have as scientists, that we may not be able to, in the inflationary cosmology, determine the quantitative physical properties of the universe prior to what's called the inflationary epoch.
So you're saying for the pendulum in that epoch, we can't, because you can infer things about the pendulum before you showed up to the room in our current epoch, correct?
Right. Yeah. So if you look at it right now, but if I said, well, when will it stop oscillating? So that depends on how much energy it got initially. And you can measure its dissipation, its air resistance. You had infrared camera. You could see it's getting hotter maybe. And you could do some calculations. But to know the two things in physics to solve a partial differential equation are the initial conditions and the boundary conditions. Boundary conditions, we're here on Earth. It has a gravitational field. It's not going to excurse or, make excursions, wildly beyond the length of the pendulum. It's not, it has simple properties. And this is in other words, you can't tell me, when did the solar system start orbiting in the way that it does now? In other words, when did the moon acquire the exact angular momentum that it has now? Now, that's a pretty pedestrian example, but what I'm telling you is that the inflationary epoch purports and is successful at providing a lot of explanations for how the universe evolved after inflation took place and ended, but it says nothing about how it itself took place. And that's really what you're asking me. I mean, you don't look, what you care about, like Big Bang nucleosynthesis and the elements got made and these fusion reactors and the whole universe was a fusion reactor. But don't you really care about what happened at the beginning of time, at the first moment of time? And the problem is we can't really answer that in the context of the Big Bang. We can't answer that in the context of these alternatives. So you asked me about some of the alternatives. So one is aeon theory, the conformal cyclic cosmology of Sir Roger Penrose. Another one was really popular in the 60s and 70s until the discovery of the primary component of my research field, the cosmic microwave background radiation, or CMB, the 3 Kelvin all-pervasive signal that astronomers detected in 1965. That kind of spelled the death knell, in some sense, to what was called the quasi-steady state universe. Mm-hmm. And then there was another a model that kind of came out of that. You hear the word quasi, so it's not steady state. Steady state means always existed. That was a cosmology Einstein believed until Hubble showed him evidence for the expansion of the universe. And most scientists believed in that for millennia. Basically, the universe was eternal, static, unchanging. They couldn't believe that after Hubble, so they had to append onto it, concatenate this new feature that it wasn't steady, it was quasi-steady. So the universe was making a certain amount of hydrogen every century in a given volume of space. And that amount of hydrogen that was produced was constant. But because it was producing more and more every century, as centuries pile up and the volume piles up, the universe could expand. And so that's how they developed.
But slowly.
Very slowly. And it doesn't match observational evidence. But that is an alternative.
By the way, did Einstein think the steady state universe is infinite or finite? Do you know?
I would assume that he thought it was infinite because there was really, if something had a no beginning in time, then it would be very unlikely we're in like the center of it, or it's bounded, or it has, in that case, a finite edge to it.
I wonder what he thought about infinity, because that's such an uncomfortable.
He has this silly joke. I'm sure you're familiar with his silly joke, right?
What's that?
His silly joke was that there are only two things that are infinite: the universe and human stupidity. And I'm not sure about the universe. So,
well, me saying I'm not aware of the joke is a good example of the joke. It's very meta. Okay, so all right. So sorry, you were saying about quasi
all the alternatives,
all the alternatives in the quasi steady state,
and the most kind of promising. Although I hate to say that, people say like, "What's your favorite, alternative?" Right?
This is not investment advice.
Inflation is not transitory; it is quasi permanent. So a very prominent.
Sorry to interrupt. We're talking about cosmic inflation, so calm down, cryptocurrency folks.
That's right. Although the first Nobel Prize and one of the first Nobel Prizes in economics was awarded for inflation, not of the cosmological kind. So most people don't know that inflation has already won a Nobel Prize.
It's a good topic to work on if you want a Nobel Prize. Doesn't matter the field.
Exactly. It's time, translation, invariant. So when we look at the alternative that's called the bouncing or cyclic cosmologies, these have serious virtues. According to some. One of the virtues to me, just as a human, I'm just speaking, as a human, one of the founders of the new version of the cyclic cosmology called the bouncing cosmology is Paul Steinhardt. He's the Einstein Professor of Natural Sciences at Princeton University. You may have heard of it. And he was one of the originators of what was called new inflation. In other words, he was one of the founding fathers of inflation, who now not only has no belief or support for inflation, he actively claims that inflation is baroque, pernicious, dangerous, malevolent, not to science, not just to cosmology, but to society. So here's a man who created a theory that's captivated the world or universe of cosmologists, such as it is. It's not a huge universe, but there are more podcasters than cosmologists. Some do both, but this man created this theory with collaborators, and now he's like, I joke, I'm like, Paul, you're denying paternity, like you're like a deadbeat dad. Now you're saying like inflation is bogus, but he doesn't just attack. See, this is what's very important about approaching things as an experimentalist. You got a lot of theorists on, and that's wonderful, and I think that's a huge service. An experimentalist has to say no. He or she has to be confident to say, like, I don't care if I prove you right or I prove your enemy wrong or whatever. We have to be like exterminators, and nobody likes the exterminator until they need one, right? Or the garbage collectors, right? But it's vital that we be completely kind of unpersuaded by the beauty and the magnificence and the symmetry and the simplicity of some idea. Like inflation is a beautiful idea, but it also has consequences. And what Paul claims, I don't agree with him fully on this point, is that those consequences are dangerous because they lead to things like the multiverse, which is outside the purview of science. And in that sense, I can see support for what he does, but none of that detracts from my respect for a man. Imagine like, Elon comes up with this like really great idea, space, and then he's like, oh, actually, it's not going to work. And, but like, here's this better idea. And he's like, SpaceX is not going to work, but he's now created an alternative to it. It's extremely hard to do what Paul has done. Doesn't mean he's right. Doesn't mean I'm going to like have more and more attention paid to it because he's my friend or because I respect the idea or I respect the man and his colleague, Anna Aegis, who works really hard with him. But nevertheless, this has certain attractions to it. And what it does most foremost is that it removes the quantum gravity aspect from cosmology. So it takes away 50% of the motivation for a theory of quantum gravity. You talked a lot about quantum gravity. You talked to eminent people on the show. Always latent in those conversations is sort of the teleological expectation that there is a theory of everything. There is a theory of quantum gravity, but there's no law that says we have to have a theory of quantum gravity.
So that kind of implicit expectation has to do ultimately with the inflationary theory. So in cosmic inflation. So is that at the core? So okay, maybe you can speak to what is the negative impacts on society from believing in cosmic inflation.
So one of the more kind of robust predictions of inflation according to its other two patriarchs, considered to be its patriarchs, Alan Guth at MIT and Andre Linde at Stanford, although he was in the USSR when he came up with these ideas, along with Paul Steinhardt, was that the universe has to eventually get into a quantum state. It has to exist in this Hilbert space, and the Hilbert space has certain features, and those features are quantum mechanical, endowed with quantum mechanical properties. And then it becomes very difficult to turn inflation off. So inflation can get started, but then it's like one of SpaceX rockets. It's hard to turn off a solid rocket booster, right? It continues the thrusting, and you need another mechanism to douse the flames of the inflationary expansion, which means that if inflation kicks off somewhere, it will kick off potentially everywhere at all times, including now, spawning an ever-increasing set of universes. Some will die stillborn, some will continue and flourish, and this is known as the multiverse paradigm. It's a seemingly robust consequence, not only of inflationary cosmology, but more and more we're seeing it in string theory as well. So that sometimes two branches coming to the same conclusion is taken as evidence for its reality.
So one of the negative consequences is it creates phenomena that we can't that are outside the reach of experimental science.
Yeah.
Or is it that the multiverse somehow has a philosophical negative effect on humanity? Like it makes us maybe it makes life seem more meaningless. Is that where he's getting at a little bit, or is it not reaching that far?
Well, no, I think those are both kind of perceptive. The answer is a little both, because in one sense, it's meant kind of to explain this fine-tuning problem that we find ourselves in a universe that's particularly fecund. It has features consistent with our existence, and how could we be otherwise? The sort of weak anthropic principle. On the other hand, a theory that predicts everything, literally everything, can be said to predict nothing. Like if I say, Lex, you've been working out, you look like, you haven't, it's great. You look like you're, about somewhere under 10,000 kilograms. You're like, all right, yeah, you're right, but that's horribly imprecise. So what good is that? That's meaningless. I don't contribute any what's called surprise or reduction in entropy or reduction of your ignorance about the system, or you know exactly how much you weigh. So me telling you that tells you nothing. In this case, it's basically saying that we're living in a universe because the overwhelming odds of our existence dictate that we would exist. There has to be at least one place that we exist. But the problem is it's a manifestation of infinity. So humans, and I'm sure you know this from your work with AI and ML and everything else, that humans, as far as we know, really are the only entities capable of contemplating infinity, but we do so very imperfectly, right? So if I say to you, like, what's bigger, the number of, water molecules in this thing or the number of real numbers? Or if I say, what's bigger, the number of real numbers or rational numbers? They're all different classifications of the amount of infinities that there could be. Infinity to the infinity power. We have kids someday, they'll tell you, I love you infinity. You have to come back, I love you infinity plus one, right? So, but the human brain can't really contemplate infinity. Let me illustrate that. They say in the singularity, the universe had an infinite temperature, right? So let me ask you a question. Is there anything that you can contemplate in the Einstein's little quip aside, that's infinite? Like a physical property, density, pressure, temperature, energy, that's infinite. And if you can think of such thing, I'd like to know it. But if you can, how does it go to infinity minus one? The opposite direction I go with my kids. How does it go from to half of infinity? Because that's still infinity. How did it cool down? How did it get more and more tenuous and rarefied? So now it's only infinity over 2 in terms of Pascal.
Less infinite, more infinite. Yeah, I mean, it's that's one of the biggest troubling things to me about infinity is you can't truly hold it inside our minds. It's a mathematical construct that doesn't. It feels like intuition fails, but nevertheless we use it nonchalantly, and then use, like physicists, they're incredible intuition machines, and then they'll play with this infinity as if they can play with it on the level of intuition as opposed to on the level of math. Maybe it's something cyclical. You can imagine infinity just going around the same, kind of like a Mobius strip situation. But then the question then arises: how do you make it more or less infinite? yeah, all of that intuition fails
Yeah.
completely.
And I mean, how do you represent it in a computer, right? It's either some placeholder for infinity, or it's 1 divided by the smallest, possible, real number that you can represent in the memory.
Well, that's basically my undergraduate study in computer science is how to represent a floating point in a computer. I think I took 17 courses on this topic. It was very useful.
So I came to the right place. But in terms of what a physicist will mean, and you're right. I mean, physicists will blithely, nonchalantly subtract infinity, renormalization, and do things to get finite answers. And it's miraculous. But at a certain point, you have to ask, well, what are the consequences for the real world? So one of them, you ask, what's the problem? Does it make us more meaningless? They purport, many of the people that support it, like Andre Linde. In fact, Andre Linde says, you have a bias, you, Lex, me, Brian, you have a bias that you believe in a universe, but shouldn't you believe in a multiverse? What evidence do you have that there's not so he turns it around. Whereas Paul Steinhardt will say, no, if anything can happen, then there's no predictive power within the theory, because you can always say, well, this value of the inflationary field did not produce sufficient gravitational wave energy for us to detect it with BICEP or Simon's observatory or whatever. But that doesn't mean that inflation didn't happen. And that's logically 100% correct. But it's like kind of chewing, Wonder Bread. I apologize if they're one of your sponsors, but
Wonderbread/Lex.com.
Type in code KLEB, right? Isn't it KLEB? That's my favorite Russian word. It's like, would you like a piece of KLEB?
By the way, even that word "chleb," which means bread in Russian, as you say it, like you're jokingly saying it now, it made me hungry because it made me remember how much I loved bread when I was in the Soviet Union. When you were like hungry, that was the things you dreamed about. I don't know.
What's amazing is how many of the Soviet scientists contributed to so much of what we understand today, and they were completely in hiding. Like, there was no Google. They couldn't look up on Scholar. Yeah. They had nothing. They had to wait for journals to get approved by the Communist Party to get approved. And only then, if they weren't a member of some class, I'm sure like Jewish scientists, you had a passport. It said Jew on your passport.
Yeah.
And Zeldovich, the famous Yakov Borisovich Zeldovich, he was the advisor, one of my advisors, Alexander Polnareff. And he had to, only because he was like at a Nobel level and, was one of the fathers of the Soviet atomic bomb program, could he even get his Jewish student, he was Jewish too, but only by virtue of his standing, of his intellectual accomplishments, would they give him the dispensation to let his student, travel to Georgia or something. And it makes what we complain about, I complain about academia, and it's like, oh, well, what can I talk about? We have no idea of how good it is. And that they were able to create things like inflation, completely isolated from the West. I mean, some of these people didn't meet like people like Stephen Hawking until, he was almost dead. And they just learned this thing through smuggled in, it's a work of heroism, especially in cosmology. There's so many cosmologists that worked incredibly hard, probably because they were working they could pass off as, well, we're doing stuff for the atomic bomb program as well, which they were.
At the same time, there is interesting incentives in the Soviet system that maybe we can take this tangent for a brief moment. That because there's a dictatorship, authoritarian regime throughout the history of the 20th century for the Soviet Union, science was prioritized. Mm-hmm. And because the state prioritized it through the propaganda machine, through the news and so on, it actually was really cool to be a scientist. Yeah. Like, you were highly valued in society, maybe that's a better way to say it. And I would say, you're saying like we have it easy now. In that sense, it was kind of beneficial to be a scientist in that society because you were seen as a hero. Yeah. As there's
Zeldovich was hero of the Soviet Republic,
and that there's positives to that. I mean, I'm not saying I would take the negatives with the positives, but it is interesting to see a world in which science was highly prized in a capitalist system, or maybe not capitalist. Let's just say the American system. The celebrities are the athletes, the actors and actresses, maybe business leaders, musicians, and the people we elect are sort of lawyers. Yeah. Right. So it's interesting to think of a world where science was highly prized, but they had to do that science within the constraints of always having Big Brother watching. It's
Yeah. The same in Germany. Germany had, highly prized science. I mean, one of the most famous, tragic to me cases is Fritz Haber, who invented the, Haber-Bosch process that allowed us to, I don't know, have you eaten yet? You look, I mean, I know you fast, intermittent fast every day, and you do that. I said chleb and you got a little drool, but
he says I'm lifting and I look slim. This is amazing. I'm going to clip this out and put it on Tinder. I think that's a website.
You got to swipe left or right for that. I don't know. But when you think about what he did and created the fertilizer process that we all enjoy and we eat from every day, he was a German nationalist first and foremost, even though he was a Jew. And he personally went to witness the application of ammonia chlorine gas applied during trench warfare in 1916 in battles in Brussels and whatever. And they had a whole cadre of Nobel laureates in chemistry and physics, that would go and witness these atrocities. But that was also, they were almost putting science above, I don't want to say human dignity, but of the fact that he would later be suppressed, and actually some of his relatives would die in Auschwitz because of the chemical that he invented, also called Zyklon B. And so it's just unbelievable. So I feel like that does have resonance today in this worship of science, and listen to science and follow the science, which is more like scientism. And there is still a danger. I always say, just because you're an atheist doesn't mean you don't have a religion. Just because you in my case, in my books, I talk a lot about the Nobel Prize. It's kind of like a kosher idol. It's something that you can worship. It doesn't do any harm, and we want those people that are so significant in their intellectual accomplishments, because there is a core of America and the Western world in general that does worship and really look at science, predominantly because it gives us technology. But there's something really cool about that, and so, for me, it's hard to find that balance point between looking to science for wisdom, which I don't think it has. They're two different words, but also recognizing how much good and transformative power, maybe our only hope, comes from science.
You opened so many doors, because you also bring up our Ernest Becker in that book. So there's a lot of elements of religiosity to science and to the Nobel Prize. It's fascinating to explore, and we will. And we still haven't finished the discussion of the beginning of the universe, which we'll return to.
Yeah.
But now, since you opened the book, wow, pun unintended, of losing the Nobel Prize, can you tell me the story of BICEP, the background imaging of cosmic extragalactic polarization experiment, BICEP 1 and BICEP 2, and then maybe you can talk about BICEP 3. But the thing that you cover in your book, the human story of it, what happened?
Yeah, that book is, in contradistinction to the second book, that's like a memoir. It's really a description of what it's like to feel, what it feels like to be a scientist, and to come up with the ignorance, uncertainty, imposter syndrome, which I cover in the later book in more detail, but to really feel like you're doing something and it's all you think about. It is all consuming, and it's something I couldn't have done now because I have too many other wonderful, delightful demands on my time. But to go back to that moment when I was first captivated by the night sky as a 12-year-old, 13-year-old, and really mixed together throughout my scientific story has always been wanting to approach the greatest mystery of all, which I think is the existence or non-existence of God. So I call myself a practicing agnostic. In other words, I do things that religious people do, and I don't do things that atheist people do. And I once had this conversation, with my first podcast guest, actually. I shouldn't say, I was just having a conversation with Freeman Dyson. Yeah. But he was actually my first guest.
Yeah.
And I miss him.
Name drop,
yes. I'm sure there's going to be plenty of comments about
So in case people don't know, Brian Keating is the host of Into the Impossible podcast, where he's talked to some of the greatest scientists in history of science, physicists, especially in the history of science.
So when I talked to Freeman, I said, Freeman, you call yourself an agnostic too. Can you tell me something like what do you do on Sundays? Do you go to church? He's like, no, I don't go to church. And I'm like, well, imagine there was like an intelligent alien, and he was looking down, or thing was looking down, and it saw Freeman. And on Sundays, like a group of people go to church, but Freeman doesn't go to church. And then there's another group of people that don't go to church, and those are called atheists. But Freeman calls himself an agnostic, but he does the things that like Richard Dawkins, he doesn't go to the same church that Richard Dawkins doesn't go to, right? So I said, how would you distinguish yourself if not practice? So I'm a behaviorist. I believe you can change your mentality. You can influence your mind via your bodily, physical actions. So when I was a 12-year-old, I got my first telescope. I was actually an altar boy in a Catholic church, which is kind of strange for a Jewish kid who grew up in New York. Maybe we'll get into that, maybe not. But I was just fascinated by these.
Can we get into it for a second?
Okay, yeah. All right, let's go.
All right, let's go there.
All right,
let's go to Baby Brian or young Brian,
the new sitcom on CBS. Young Brian, born to two Jewish parents. My father was a professor at SUNY Stony Brook. He was a mathematician, eminent mathematician, and my mother was an eminent mom and brilliant English major, etc. And they raised us, but they were secular. They, we'd go to, I always joke, we'd go to synagogue, 2 times a year on Christmas and Easter. No, we would go, Yom Kippur, Rosh Hashanah, right? That's the typical 2-day a year Jews. And, we'd have matzahs once a year on Passover. And that was about it. And for years I was like that until my parents got divorced. My mother remarried, and she married an Irish Catholic man by the name of Ray Keating. My father's name is James Axe. So when she remarried Ray Keating, I was immediately adopted. I'm actually adopted into the Keating family. And he had 9 brothers and sisters, and just warm and gregarious. They, did Christmas and Easter. It was one of the most wonderful experiences I had. And I do things with great gusto. Whatever I do, I want to take it all the way. So to me, that meant really learning about Christianity, in this case, Catholicism. So I was baptized, confirmed, and I said, I want to go all the way. I became an altar boy in the Catholic Church.
And you're going to be the best altar boy there ever was.
I had like serious skills. You pass that collection basket. I could push people and get them to 2x their contributions. But in this case, I was 13. I don't know if you remember, when you were 13, but if you extrapolate the next level up, it's like you go graduate student, postdoc, professor. The next level up from, confirmation, altar boy is priest. And I don't know if you're aware of this, but priests are not entitled to have relations with women. And as a 13-year-old boy, kind of like future casting what life's going to be like for myself if I continue on my path, I found it,
the math didn't add up.
That's right. There was a serious gap in that future. And instead, when I should have been preparing for my bar mitzvah, as most Jewish boys would be, a 12, 13-year-old boy, I actually got a telescope and became infatuated with all the things you could see with it. It wasn't bigger than that one over there that your hedgehog's looking through. Is that hedgehog?
It's a hedgehog in the fog. I should mention, and we'll go one by one, these things. You've given me some incredible gifts. Maybe this is a good place to ask about the telescope that put some clamps on and let the hedgehogs look. And using
now you're officially an experimental astrophysicist, by the way.
Why experimentalist versus an engineer?
Because you assembled this telescope, you gave it a mount, and you connected it to a very powerful.
But there's no experiment going on. It's just engineering for show.
Okay,
it's very shallow. So experimenters taking it to the next level and actually achieving something. Here, I just built a thing for show.
Well, that's always a joke. People say, "Oh, you're an experimental cosmologist." So I'm like, "Yeah, I build a lot of universes." Most of my time is putting clamps on things, soldering things. It's not actually doing the stroking of my non-existent beard, contemplating the cyclic versus the bouncing cosmological model.
Yeah,
right?
And just like most of robotics is just using Velcro for things.
Right, yeah. It's not like having dancing dogs and whatever, right? So telescope.
Yes, this telescope. What's the story of this little telescope?
So this telescope's a very precious thing in some ways, a symbol of what got me into, what brought me all the blessings I have in my life came from a telescope. And I always advise parents or even people for themselves. You right here, wherever we are, biggest city on earth, Manhattan, where I was growing up as a 12-year-old outside of Manhattan. You can see the exact same craters on the moon, the same rings of Saturn, the same moons of Jupiter, the same phases of Venus. You can see the Andromeda Galaxy, Lex, 2.5 million light years away from Earth. And you can do that with that little thing over there. Or one that's a little more expensive. Get one that has a mount, and you can attach now your smartphone. What the hell is that? I wouldn't have known what that was in 1984. And with that, you can do something that no other science, to my knowledge, can really replicate. Maybe biology in some sense, but you can experience the physical sensation that Galileo experienced when he turned a telescope like that to Jupiter and saw these 4 dots around it, or that Saturn had ears, as he called it, or that the moon was not crystalline, polished, smooth, and made of this heavenly substance, the quintessent substance, right? So where else can you be viscerally connected with the first person to ever make that discovery? Try doing that with the Higgs boson. Get yourself an LHC and smash together, high luminosity, call up Harry Cliff and say, I want to replicate. How did you feel? He didn't feel anything. None of them felt anything. It took years to compile it. You can't do it. But with this, you can feel the exact same emotions.
That's fascinating. It's almost like maybe there's another one like that is fire.
Yes.
Like when you build a bonfire, like can you actually get it? See, if you use a lighter, I think if you actually, by rubbing sticks together or however you do it without any of the modern tools, that's probably what that's like.
Yeah.
And then you get to experience the magic of it. Of what like early humans, Homo sapiens,
you feel
did.
what Og felt when he did it that first time.
By the way, is this a gift?
This is a gift, of course.
Okay,
you need a little bit of a swag upgrade, so I got you some gifts.
Yeah, this is I'm pulling a Putin. Like, asked if this is a gift, making it very uncomfortable for you to say. Not really.
This is actually my childhood telescope here.
But now I'm keeping it.
That's all right. So looking through this telescope
was when your love for science was first born.
Changed my life, because not only was I doing that, I was replicating what Galileo did, but I'm 100% not comparing myself to Galileo Galilei. Okay, if there's any confusion out there, but I did replicate exactly what he did, and I was like, holy crap, this is weird. Let me write it down. So it had another effect, which all good scientists, budding scientists should do, and all parents should do. Get your kid a book, a little notebook, tape a pencil to it. Write down what you see, what you hypothesize, what you think it's going to be. Not like in the high school, hypothesis, thesis, but just like, wow, how did I feel? Better yet, astronomy is a visual science. Sketch what you see. The Lagoon Nebula, the Pleiades 7 Sisters. You can see them anywhere on Earth. And when you do that, again, you're connecting 2 different hemispheres of your brain, as I understand it, and you're connecting them through your fingertips. You literally have the knowledge in your fingertips, in your connection between what you see, what you observe, and what you write down. Then you do research, right? The goal of science is not to just replicate what other people did, is do something new. And that's why we call it research and not just like studying, Wikipedia. And in so doing, you start to train a kid at age 12 or 13 for $50. It's unbelievable. And now we can do even better because you got share it on Instagram or whatever. And you can, by doing so, have an entree into the world of what does it really mean to be a scientist, and do so viscerally. I often say, I was taught this by my English teacher, Mrs. Tompkins, in 9th grade, that the word educate, it doesn't mean to pour into. Let me pour in some facts into Lex. And, it's not like machine learning that you're just showing like billions of cats, or, you're not like forcing it in, you're bringing it out. It means to pour out of, in Latin, educare. And what more could a teacher want than to have something that the kid is just like gushing? No, you're not going to see like
to inspire the kid.
Yes,
inspire.
Yes.
Shout out to Mrs. Tompkins.
Yeah, Mrs. Tompkins. She's watching. Yeah, she's a big fan. Me, she doesn't care for, but you.
Yeah, excellent. We take those we love for granted. This is in Manhattan.
This is in Westchester County, New York.
Okay,
yeah.
got it. So but then that's where the dream is born.
Yeah,
but then there is the pragmatic journey of a scientist. So going to university, graduate school, postdoc, and all the way to where you are today. What's that? What are some notable moments in that journey?
So I call that the academic Hunger Games, because it's like you're competing against like these people, who are just getting smarter all the time as you're getting smarter all the time. They want to get into a fewer and fewer number of slots. Like there's fewer slots to get into college than in high school. There's fewer slots in graduate school. There's very fewer slots to be a postdoc, and many, maybe infinitesimal number. We just did a faculty search at UC San Diego, 400 applicants for one position. It's almost getting impossible. Like I almost can't conceive of doing what these new brilliant young people applying to become an assistant professor at a state university that they're doing. Like it takes so much courage to do that. So I went from, this kid in New York, thinking I would never be a professional astronomer, because I didn't know any. I'd never seen any. I didn't even know that they existed. And I thought, who the hell's going to pay me to look at the stars? Like, will they pay me to be like an ice cream taster? Like, it's just not something I could conceive of getting paid to do, even if I had the brilliance to do it, which I didn't feel I did. And then I went to graduate school, and during graduate school, I had this kind of on again, off again relationship with my father. And I knew that he was a mathematician. He had left and gotten remarried himself and moved across the country. I didn't see him for 15 years. And in that time, I learned a lot about him. And I learned that he had gotten very interested, not in pure mathematics, which he had been a number theorist and contributed seminal work on Diophantine equations, which play a role in Turing's work, you may have seen. But anyway, he had become interested, turned completely away from that into the foundations of quantum mechanics and relativity, which is physics. And by that time, I was at Brown University, and I was, thinking, oh, maybe I'll be condensed matter physicist or experimentalist. I never thought I'd be a theorist, and I'm not a theorist, so it was pretty prescient. And but it always appealed to me, like, why not do what made me happy as a 12-year-old? Like, we often forget about like those, primitive things about us are probably the most sustainable, durable, and resilient attributes of our character. So with my own kids, I look like, what are they interested in now when they're young? And it doesn't mean that's what they're going to do. I mean, some of them want to play Fortnite, like professional Fortnite play, which there are, but the odds of that is less than the odds of being a professor.
Can I ask you, is your father still with us?
No.
Just in a small tangent.
Yeah.
Do you miss him? Do you think about him? Does his mathematical journey reverberate through who you are?
Oh, yeah, absolutely. I mean, it did in very many ways. And he's been gone for a long time now. Thinking back to that time with him, he must have instilled some capacity for me to only want to spend my time, which is a limited quantity. I don't think it's the most limited quantity. Maybe we'll talk about that later. But to go into only the most challenging, interesting things with the limited time that we have while we're alive. And for him, it was the foundations of quantum mechanics. For me, it was the foundations of the universe and how did it come to be. And I felt like, well, people have been trying since Einstein to outdo Einstein, really haven't made great progress in the foundations of quantum mechanics. But this is an exciting time. The Kobe satellite had just released its data that the universe had this anisotropy pattern. Stephen Hawking called it like looking at the face of God and so forth. And so it seemed like this is a good golden age for what I'm going to do and what I'm most interested in. But always throughout that, I wanted to understand. I didn't want to be a wrench monkey. No offense to people that just do experiment.
And no offense to monkeys.
No offense to monkeys. That's right. This little guy. Sorry, man. But thinking back to what animates me, it's not doing the engineering as much as it is getting the data. But there's a lot of steps. I want to be the guy understanding what made the universe produce the signal that we saw. So I always joke with my theorist friends, who call me a closeted theorist, like I want to be, what they call a guy who hangs out with musicians, a drummer. So I want to be like that for physics, right? Like for theoretical physics. I want to be like the guy who doesn't do new theory, but understands the theory that the new theorists are doing.
I love that formulation of a theorist is understanding the source of the signal you're getting. Like signal is primary. Yeah. Like the thing you measure is primary, and theory is just the search of explaining how that signal originated. But it's all about the signal. I mean, I see the same search for the human mind and like neuroscience in that same kind of way. It's ultimately about the signal, but you kind of hope to understand how that signal originated. That's fascinating. Yeah. That's such a beautiful way to explain experimental physics, because it ultimately at the end of the day is all about the signal.
Yeah, and maybe those two things, the neuroscience and the cosmos, not getting too romantic, but yeah, maybe they're linked in some fundamental way. Maybe they're some fundamental cosmic consciousness. But
we're gonna get to that.
Yeah. No, we definitely have to get to that. But getting back to so my origin story. So I always say, like, and I want to try this on you. You said you wouldn't answer any of my questions, but I'm going to ask you some questions. What's the most important day on the calendar? Don't tell me the date, but what's the most important day to you every year?
Do I have to answer, or do I have to think about
No, just answer. Like, you don't have to tell me the exact date on the calendar. It could be like your mistress's, birthday or whatever. But
I have so many, I lose track. Even though I'm single, how does that even make sense?
I know.
Okay, I'm sorry. So a day, like a month and a day. Yeah, I mean, for me, it would be December 31st.
Yeah. So I was going to say New Year's Eve, New Year's Day. Some people say birthday, anniversary, kid's birth. They're usually signifying beginnings and ends, right? January means the portal between the God was the portal between the beginning and the end. So you're looking back, maybe because you're Russian, like the death side, the light side, looking forward into January, the beginning, right? Um, so everybody's most important day is usually some beginning or something significant. For me, it was studying the most significant thing of all. It's like, when did the universe get born, as I said before? And I didn't think there was some mental obstruction that I didn't realize that I could get past, because I didn't think like anybody does it. Like, I knew astronomers knew these answers, like the universe at that time between 10 and 20 billion years old. Now we know it's 13.872 billion years old. It's incredible, the 5-digit, per significant five.
What is it again?
13.872 billion years. 872 million.
So is there a lot of plus or minus on that? Is it, what are the error bars on that?
For me, I'm 50. So it would be the equivalent of you looking at me and telling me within 12 hours how old I am.
Yeah.
So 0.5% level accuracy.
There's a confidence behind that?
Oh, yeah. I mean, there's this significance. Yeah. No, it's extremely well measured. I mean, it's one of the most precise things that we have. In contrast to, again, 25 years ago, we didn't know if the universe was 10 billion or 20 billion years old, but there were stars in our galaxy that were believed to be, as they are, about 12 billion years old, or in the universe that were 12 billion. So that would be like you being older than your father. It was embarrassing.
Can we actually take a tangent on a tangent on a tangent on a tangent? How old is the universe? Can you dig in onto this number? How do we know currently with those, I guess you said 4 or 5
significant figures,
significant digits?
So we can come about it from two different ways. One, basically they rely on the most important number in cosmology, which is called the Hubble constant. The Hubble constant is this weird number that has the following units. It has the units of kilometers per second per megaparsec. So it's a speed per distance, which means you multiply it by distance and you get a speed. And what is the speed you're measuring? Well, you're measuring the speed of a distant galaxy at many megaparsecs away. So a galaxy at 1 megaparsec away, this isn't actually strictly true because of local gravitational effects. But if you go out, say 1 megaparsec away, I would say that galaxy is moving 72 kilometers per second away from you. And every galaxy, except for the very most local group surrounding us, maybe a half a dozen galaxies, out of 500 billion galaxies to perhaps a trillion galaxies. So 12 out of that number are moving towards us. The rest are moving away from us. So that number, if you invert it, if you say, well, when did those things last touch each other, all those galaxies? Now they're really far apart. We know how fast they're moving away. It's a very simple algebra problem to solve. When were they touching? That's where you get that number from.
So there's the local 12 and then the rest.
Ignore the 12, yep.
And then ignore the 12 and then look at the others and then solve the algebra problem. How does the stuff in the beginning, the mystery of that beginning epoch change this calculation of?
Very little, because actually we understand how there's some other ingredients that go into it, namely how much dark energy there is in the universe, how much dark matter there is in the universe, how much radiation, light, neutrinos, et cetera, there are, and how much ordinary matter, like we're made up of, neutrons, protons, croutons.
Okay, so let me...
Morons.
It appears that the universe is bigger than it is older. How does that make sense?
Oh, yeah. So you're talking about the fact that we can actually see stuff in our observable universe that's located at a distance that is farther than the speed of light times the age of the universe.
Yeah.
Naively, you would say that So you're right. If the universe were static, if the universe came into existence, and you can conceive of this, the universe came into a big bang in a fixed universe. So the universe just started off. Those galaxies were, they could be moving towards us, away from us, who knows? That you could say, I can see a galaxy that's at a distance of only 13.8 billion years times the speed of light. That would be true. But the fact that the light is expanding along with the expansion of the universe. So imagine there was some very distant past. We were near a galaxy. It's going to produce some light. And that galaxy is going to be moving away from us. The light's going to be getting more and more red shifted, as it's called. And it's going to be moving farther and farther away from us as time goes on. There'll be some acceleration as we get into the era of dark energy. The light signals, there'll be some cone of acceptance, if you will. from which represents all the events that we could have received information from. We can't currently communicate with that galaxy. It sent us some light, and now it's moving away, and it sent us some light. And because the space is also dragging the photons with it, if you like, the photons are being participating in the expansion of the universe. That's why they're redshifting. That we can see things out to where the universe first began expanding, not just when it began existing. And because the universe has been expanding for 13.8 billion years with no sign of slowing down yet, which is a huge surprise, serendipitous surprise, that we can see things approximately 3 times the age of the universe away from us. So we can see, let's call the age of the universe 15 billion years, just to make the math simple. We see things at 45 billion light years distance in that direction. And we see things at 45 billion light years in that direction, just turning our telescopes 180 degrees away. So that means we see things that themselves are 90 billion light years away from each other. That's sort of the diameter of the observable universe. Is there another universe beyond that? We don't know. Some conjecture there's not only one, there's an infinite number of them.
How are you emotionally okay with the fact that our universe is expanding? So like,
it's going to be like Annie Hall, like with Alvy Singer.
I grew up in the Soviet Union. We watched propaganda.
I realized that you did, yes. So there's a famous
Annie Hall? Is
Annie
that
Hall.
some kind of, what is this?
Communist Party, propagandist movie with Woody Allen. Certainly canceled, but nevertheless, back when he was not canceled yet, he made a movie called Annie Hall, in which it's a self-depiction. He's like a Larry David before Larry David was Larry David. Typical neurotic young Jew. He's in Brooklyn, and he all of a sudden tells his mother he's not doing his homework anymore. He refuses to do his homework. His mother says, why? He goes, because the universe is expanding, and it keeps on expanding. Everything will rip apart, and we'll never have anything in contact, and everything is meaningless. And I assume these are some of the topics we're going to get to. And she goes, what are you talking about? We're in Brooklyn. Brooklyn is not expanding. And that's true. Brooklyn is not expanding. The solar system is not expanding. Oftentimes I get asked, what is the universe expanding into? That's one of my favorite questions. What is it expanding into? And I say, it's actually an easy question if you think about it. You've seen your friend Elon, he goes out into space, he's got a rocket, right? What's outside of the rocket? If you take this bottle, empty out this bottle, take the cap off it, go outside the rocket, sip in some Tang, screw on the cover of it. What's in there? Is it empty?
That's just semantics, I guess. Yeah.
No, it's definitely not empty.
So you step outside the rocket?
Yeah, you're in the vacuum of space, the quote-unquote vacuum of space.
And there's no more liquid in it?
There's no more liquid in it. No, it's just a container, 1 cubic centimeter. Let's just make it simple. 1 cubic centimeter of box, and you take it out into space, outside the Falcon, whatever, right?
Yeah.
What's inside that box? It's not empty. There's actually, I'm going to say, this is going to set your friends up. There's 420 photons from the fusion of the light elements that we call the cosmic microwave background inside that box at any second.
Okay. All right. Hold on a second. What? 420. That's, I've heard of that number before. All right.
It used to be 69. But then they changed it.
Wow, physics works in mysterious ways. Okay.
In a millimeter box, it's 69.
What are we talking about here? What's in what's in the box?
I'm gonna get that's right. Let's think outside the box. No, we're thinking inside the box. So if you have every cubic centimeter of our observable universe is suffused with heat left over from the Big Bang. Dark matter particles. There's a little ordinary matter in the universe. And every cubic centimeter, there's some probability to find a proton, a cosmic ray, an electron, et cetera. There's actually an awful lot of neutrinos inside of that cubic centimeter. Now, just imagine how many cubic centimeters there are in the universe. It's enormous. That's why there's enormous numbers of particles in our universe. It's a very rich universe. But now let's zoom in on that box. So now inside that box, there might be, one, let's say there might be one ordinary matter, like a proton or an electron, a baryon, a lepton. There might be a couple hundred neutrinos, and there'll be a couple hundred photons, as I said, 420. What's between those guys? What's between the protons and the neutrinos and the photons? Like, just zoom into a cubic micron now. Like, imagine 420 things inside a box this big. It's actually pretty empty. Mm-hmm. Like, they're just zipping around in there, right? So between them, there's a lot of empty space.
And this is outside the kind of physics-based models of fields and all those kinds of things.
Yeah,
just actually asking the question of, like, what is this emptiness?
What's the particle content in the universe, in every cubic centimeter of the universe?
outside of the 420. So you have the 420.
420.
They have some, they have some mass.
Yeah. Oh, they have energy. They don't have mass. Photons don't have mass.
Energy.
That's why they don't
mass.
bring suitcases. You know that's true, right? Photons never bring suitcases with them because they're traveling light. See, I don't even get a laugh out of you. That's corny dad jokes. Okay, you'll appreciate it someday.
No, this is pretty good. It's just I'm laughing on the insides. What's in the box? What's the 420? What's between the photons?
That's what space is. That's what the universe is expanding into.
Okay, that's
nothing.
So that's the notebook on which the photons are written.
Exactly. That's beautiful.
But still, thank you. Still, I understand this, but it's still uncomfortable that if the universe is expanding, that this thing is expanding. The canvas is expanding. It's very strange. Because like if we were just sitting there still, I guess if we're in Brooklyn, nothing's expanding. So our cognition, our intuition about the world is based on this local fact that we don't get to experience this kind of expansion.
Yeah, and that intuition leads us astray. But you know that gravity is the weakest of the so-called four fundamental forces. And yet it has the longest range pervasiveness. Gravity is, we're being pulled towards the Andromeda Galaxy at some enormous rate of speed because of its massive counter-gravitational force to the force we exert on it. So gravity is enormously long range, but incredibly weak. And because of that, we can think about these effects of expansion as the relationship between as you said, the grid lines on the notebook, right? Gravity is a manifestation of the interrelationship between those points, how far they are from each other, and those can change. Those point distances can change over time because of the force of gravity. So it's weak, and what we experience as gravity is the changing of those trajectories from being rectilinear to curvilinear. That's what we experience as gravity. Well, you had this analogy when you talked to Barry Barish about a bowling ball and a trampoline, and that's almost right because it's actually, you have to visualize that now in 4 dimensions, like wrapping a trampoline at every point around the object, including on the sides, and it becomes very hard to visualize. So a lot of people use that. It's also a fraught analogy because you're using gravity, like the notion of gravity pulling something down, to explain the notion of gravity. So it's a little overburdening the analogy.
But okay, so you mentioned Barry Barish wrote the foreword to your book.
Yeah.
How do gravitational waves fit into all of this? How do they, on the emotional level, how do they make you feel that they're just moving space-time?
Yeah. So gravitational waves were the Nobel Prize for gravitational waves discovery the first time. It was discovered twice, indirectly by 2 men named Hulse and Taylor. And that was given my first year of graduate school. The day I entered graduate school almost, they announced these 2 guys won it. And the guy who won it did the work that would later win him the Nobel Prize when he was my age.
Is this in the 40s?
This is 19.
That was a joke.
Yeah, that was good. Right. That was good.
Thank you.
I got it. To a cosmologist, age means nothing. Yeah. And to a tennis player.
Not on Tinder.
That's right.
All right. Sorry.
So gravitational waves do fit in because what we're trying to do now is use the properties of gravitational waves, the analogous properties that they have to photons, that they travel at the speed of light, that they go through everything, they can go through everything, and that they're directly detectable. We're using them to try to confirm if or if not inflation occurred. Mm-hmm. So did inflation, the spark that ignited the fusion of the elements in the early part of the universe and the initial expansion of the universe, did that take place? There's only one way that cosmologists believe we could ever see that, through the imprint of these primordial gravitational waves, not these old, newcomers that Barry studies, the ones that occurred 1 billion light years away from us, 1 billion years ago. But we're seeing things that happened 13.82 billion years ago during the inflationary epoch. However, those, we cannot build a LIGO and put it at the Big Bang. So if you want to measure, let's say you have the old-time firecracker. Let's say there's a firecracker, and you want to see if it went off in the building next door to you. You can't see it, so you can't see the imprint of it, but you can hear it. And what we're trying to do is hear the effect of gravitational waves from the Big Bang, not by using a camera or even an interferometer like Barry used and his colleagues, but instead using the CMB the light, the primordial ancient fossils of the universe, the oldest light in the universe, we're going to use that as a film, quote unquote, onto which gravitational waves get exposed.
And hope you can. So, what are the challenges there to get enough accuracy for the exposure?
So the signal, as I said, is so there's 420 of these photons per cubic centimeter, and there's a lot of cubic centimeters in the universe. However, what we're looking for is not the brightness of the photon, how intense it is. We're not looking for its color, what wavelength it is. We're looking for what its polarization is.
And we'll go there. Let me just ask: are you serious about the per cubic millimeter? 420 is the number.
Centimeter.
But cubic centimeter.
Yeah.
420 is the number.
That's the number.
I wonder if Elon knows this, and if he doesn't, he will truly enjoy this.
Okay.
This is great.
Yeah, it's true.
Oh, okay. Funding secured. Excellent. So, I mean, this takes us to this story of heartbreak, of triumph, of that you described in losing the Nobel Prize. So, describe what polarization is that you mentioned.
Yeah.
Can you describe what BICEP 1 and BICEP 2 are? BICEP 3, perhaps the instruments that can detect this kind of polarization. What are the challenges, the origin story, the whole thing?
Yeah. So, well, the origin story goes back again to like a father-son rivalry. It really does. So my father won all these prizes, awards, et cetera, but he never won a Nobel Prize. And, some parents in America, they compete with their kids. Oh, I was a football player in high school. I'll show you, and whatever, wrestling, whatever. And some of it could be healthy too. But with me and my dad, it wasn't super healthy. We would compete and he was much more of a pure mathematician and I was an experimental physicist. So we had both different ideas on what was worth prioritizing our time. But I knew for sure he didn't win the Nobel Prize. And I knew I could kind of outdo him. So I feel pretty venal and kind of, minuscule kind of character-wise saying that.
The only reason you could outdo him is because the Fields Medal is given every 4 years.
And only if you're under 40, which he was.
So he's working under much more limited conditions.
That's right. So even if I had, which, spoiler alert, the book's called Losing the Nobel Prize, so I didn't do it. But I wanted to do something big, and I wanted to do something that would really just unequivocally be realized as a discovery for the ages, as in fact it was when we made the premature announcement that we had been successful.
So you were from the beginning reaching for the big questions.
Yeah. That's all I cared
about. As an experimenter, you were swinging for the fences.
That's all I wanted to do. I felt like if it's not, if it's worth spending perhaps the rest of my life on as a scientist, it better be better be interesting to me, to carry me through, to give me I always say passion is great when people say, oh, follow your passion, but it's not enough. Passion's like the spark that ignites the rocket, but that's not enough to get the rocket into space.
So then you swung for the fences with BICEP 1. What is this?
Yeah. So BICEP 1 was born out of kind of interesting circumstances. So I had gone to Stanford University for a postdoc. So an academic Hunger Games. Stanford University. Yeah, it's this small little school. It's not like that technical college in Massachusetts that you're affiliated with. Yeah. But as I went there, I was working for a new assistant professor. She had gotten there only a year before I got there, and she had her own priorities, things that she wanted to do. But I kept thinking in my spare time that I wanted to do something completely different. She was studying galaxies at high redshift, and I wanted to study the origin of the universe using this type of technology. And I realized, courtesy of a good friend of mine who's now at Johns Hopkins, Mark Haminkowski, that we didn't need this enormous Hubble telescope. We didn't need a 30-meter diameter telescope. We needed a tiny refracting telescope, no bigger than my head, less than a foot across. And that telescope would have the same power as a Hubble telescope, size telescope could have, because the signals that we're looking for are enormous in wavelength on the sky. They're enormously long, large area signals on the sky. And if we could measure that, it would be proof effectively, as close as you get to proof. There could be things that mimic it, but that we discovered the inflationary epoch. Inflation being the signal originally conceived of by Alan Guth to explain why the universe had the large-scale features that it does, namely that it has so-called flat geometry. So there's no way to make a triangle in space in our universe that has 3 interior angles that do not sum to 180 degrees. You can do that with spacecraft. You can do that with stars. You can do that with laser beams. You can do that with 3 different galaxies. All those galaxies, no matter how far you go, have this geometry. It's remarkable. but it's also unstable. It's very unlikely. It's very seemingly finely tuned. And that was one of the motivations that Guth had to kind of conceive of this new idea called inflation, 1979, when he was a postdoc also at Stanford, SLAC. And he was trying to get a permanent job. I was trying to like make my name for myself. And so I realized I could do this, but I was also being paid by this professor at Stanford to do a job for her. And I was kind of a crappy employee, to be honest with you. And then one day she couldn't take it anymore because I was like sketching notebooks and planning these experiments. And I
you had big ideas in your mind. You were planning big experiments.
Yeah.
And that was difficult to work with on a small scale for like a postdoc type of situation.
Yeah.
Where you have to, publish basic papers, deliver on some basic deadlines for a project, all those kinds of things.
And support your advisors, paying me. She was paying me.
Yeah.
And so one day I came in and it actually involved another friend of mine, an astronomer named Jill Tarter, one of the pioneers in the SETI science business of detecting extraterrestrials, which I assume you'd never like to talk about aliens, so I'm sure we won't get into aliens. But Jill was visiting Stanford, and I was like, I really want to meet her. Can you introduce me? And she said, no, in fact, you're fired, my boss. So I was like, this is possibly the best thing that could ever happen to me. I didn't know where it would lead or what would happen to it, but getting fired from this ultra prestigious university turned out to be the path. I mean, literally, it brings me here today. In that, because of that, I ended up working for another person in Caltech, which is in Pasadena, and she, my original boss, Sarah Church, she got me the job with her former advisor, a man by the name of Andrew Lang. And Andrew was like, he was like this, I don't know, like, he's like a Steve Jobs or Elon, charismatic, handsome, persuasive, idea man. Not the guy always in the lab, doing everything, but understood where things are going decades from now. And he had been involved in an experiment that actually measured the universe was flat, very close to flat, along with a preceding experiment done at Princeton by Lyman Page and other collaborators.
So the shape of the universe is flat.
The geometry of the universe is flat.
How did he do that experiment?
So he used the cosmic microwave background. And so what I said is you have to look for triangles in the universe. So you can measure triangles on Earth. You can actually, it's hard to show that the Earth is curved, but you can show the Earth is curved using triangles, mountaintops, et cetera, if you have an accurate enough protractor.
Allegedly, yeah.
Yeah. God, you're like auto-canceling. This is great. My ratings are going to go up, man. This is going to be great. Take out the
If you want actual science, go listen to Brian. If you want all of these conspiracy theories, or AKA the truth about flat Earth, listen to me.
So what he used was the following triangle. There are proto-galaxy-sized objects in the CMB. The cosmic microwave background has these patches, and so you can make a triangle out of the diameter of one of these blobs of primordial plasma, the soup that constitutes the early universe, which is hydrogen. It's very simple material. Understand hydrogen, electrons, and radiation. Very simple. Plasma physicist, son, understand it. The diameter is one base of the triangle, and then the distance to the Earth is the other two legs. So he measured, along with his colleagues at Caltech and University of Rome and that other group at Princeton, measured the angle, interior angle effectively, very, very accurately, and showed that it added up to 180 degrees.
Can you localize accurately the patches in the CMB? Can you know like where you could like trace them back location wise?
You can know where they are, but more than that, there's so many of these patches. They're about 1 square degree on the sky. The sky, you may know, a sphere has about 44,000 square degrees in a sphere. So there's literally 44,000 of these size patches over which he could do these kind of measurements to build up very good statistics. That's not exactly how they do it or how they did it in this experiment called Boomerang, but they did measure very accurately the what was called the first Doppler peak or acoustic peak in the plasma, the primordial plasma.
That's fast. So the sphere has approximately 44,000 square degrees. So to cover a sphere, that's a very kind of important data collection thing when you're sitting on a sphere and you're looking out into the observable universe. So there's a lot of patches to work with.
Yeah. And in fact, a lot of the fast kind of algorithmic decomposition of spheres and machine learning in the early 2000s, still used today, was created out of this field by data analysts using this thing called hierarchical equal area triangles called heel picks is what it's called.
And so just stitch all of this stuff together. And that's and stitch it together very accurately.
Yeah. Get high statistical significance in order to reduce the statistical errors. Very clean signal and measurement device to reduce the systematic errors. Those are the two predominant sources of error in any measurement. Those that can be improved by more and more measurement. You take more and more measurements of this table, you'll get slightly better each time, but you only win as the number of the 1 over the square root of the number of measurements. But the square root of 44,000 is pretty big. So they were able to get a very accurate measurement. Again, it's not exactly how they did it. They also have to do a Fourier analysis, decompose that, do a power spectrum, filtration, windows. There's a lot of work that goes into it, image analysis, and then comparing that with cosmological parameters. Very simple model, just 6 different numbers that go into a model that made a prediction. And one of those is the geometry of the universe pops out. And that is the universe has 0 spatial curvature. And that was called boomerang. So he had just come off of this. Now, let me remind you, who was the first person, to measure the curvature of the Earth? It's a guy named Aristophanes in the, whatever, lived around Aristotle's time. His name is in the history books. So this guy, Andrew Lang, I was like, he's like the next Aristophanes. Like, I just wanted to work for this guy. He was clearly had this brand. He was about 40 at the time. California Scientist of the Year. I was sure he was going to win a Nobel Prize for that. And I knew that he, so I went down to Caltech to give my job talk. And he said, I love it. You got a job. And before I could even, before he finished the sentence, I said, I'll take it. It was too good to be true. And I started working there at Caltech, and slowly but surely, because Caltech's a rich private university, at that time run by a Nobel Prize winner by the name of David Baltimore, he just wrote us a check. Baltimore wrote us a check and said, get started on this idea. And so we started coming up with the idea for what I later named BICEP, background imaging cosmic extragalactic polarization, which is kind of ironic because we ended up measuring galactic polarization. We'll get to that in a minute. But along the way, the idea was very simple. We're going to make the simplest telescope you can possibly make, which is a refracting telescope. Your eyes, you have 2 refracting telescopes in your head. Only way, forward is making things more complex, right? And when you make things complex in science, you introduce the possibility for systematic errors. And so we want to build the cleanest instrument. It turns out the cleanest instrument you can build in astronomy is a refracting telescope. We also had to, unlike that telescope or Galileo's, we had to use very sensitive detectors that were cooled less than 1/20th of the temperature of the cosmic background itself, which is the coolest temperature in the whole universe. So we had to cool these down to about 0.1 or 0.2 degrees Kelvin above absolute zero. To do that, we needed to put it inside of a huge vacuum chamber and suck out all the air molecules and water molecules and take it to a very, very special place called the South Pole, Antarctica, from which I retrieved for you a patch. There it is over there. So when you go there, you get these bright red jackets.
Bright, oh yeah.
You fly
As
down.
somebody who was born in the Soviet Union, we obviously like to call it red. United States Antarctic Program, the National Science Foundation.
And the base is called the Amundsen Scott South Polar Station. So it's a little known fact of geopolitics that whatever country occupies a region has ownership over it. Now, there is a treaty in Antarctica. You can't use it for military purposes, for mining, et cetera, et cetera. But I don't know if you know, but about 12 years ago, Putin sent a submarine to the North Pole. Now, there's no land at the North Pole, right? Mm-hmm. So what did he do? He stuck it on the ocean underneath. But the South Pole is on a continent called Antarctica, which was first reached about 110 years ago, the first time in human history. Antarctica means the opposite of the bear. It means like no bears there. Like basically opposite of where polar bears are. Arctic means polar bear. That's where in Greek.
Oh, I did not know that.
Yeah.
Fascinating.
So Antarctic means the opposite place of that. So humans never even saw it, let alone went to the South Pole, which is kind of in the middle of that continent. We wanted to take this telescope somewhere extremely dry. It turns out the Sahara Desert, San Diego, Texas, there's no place like the South Pole or Chile. Those are the 2 premier places on Earth. Mm-hmm. Of course, you'd like to go into space. There's no water in space.
So it's not about cold. It's about dry.
Exactly. So that's why, for example, you can take this vodka and you could put it in this cup, right? And we could take it over to a microwave somewhere and heat it up. Mm-hmm. After 3 minutes, the water's boiling. You can't touch it. Take it from me. Don't touch it. But you can touch the mug and take it out if you want to, right? Why? Because the mug is totally bone dry. But the microwaves get absorbed by the water molecules because water molecules resonate exactly at these microwave frequencies. So we don't want these precious photons 420 of them traveling per cubic centimeter from the Big Bang itself to get absorbed in some water molecule in the Earth's atmosphere. So you take it to a place with the fewest number of water molecules per square centimeter of surface area. And that happens to be either Chile, where my other project, the Simons Observatory, is located, or you take it to the South Pole. We took it to the South Pole and spent a couple of months of my life down there. And it's like being on Hoth. It's a completely otherworldly environment. Ice, planar, flat as a pancake. And the buildings are built up on stilts. They're built up because the snow will otherwise cover them over. The nearest medical facilities are 4,000 miles away. If you have any issues with your wisdom teeth, they yank them before you go down there. If you have any issues with your appendix, they'll cut it out of you before you go down there. The Russians at Vostok base, not too far away, about 600 miles away. The doctors there, there's a famous picture of one of them operating on himself, taking out his own appendix in the middle of winter by himself.
So harsh conditions, science in the harshest of conditions.
On Earth, at least. And we go to those great lengths because it's a pristine environment to observe these precious photons. And we built this telescope, and it weighs, tens of thousands of pounds. And it had to scan the sky almost like it's a robot. I mean, it's scanning the sky almost unattended. It needed, we have a guy who spends a year of his life down there, a girl who spends a year of their life down there. They're called winter overs. They arrive in sometimes as early as November, and they don't leave until the following December. And we always joke, we'll pay you $75,000. You just have to work for one night of your life. That's all. But it's a long night. And what BICEP is, and I couldn't bring my polarized sunglasses here, so I brought these actual polarizers here. So if you take this and put in front of your telescope there, you have now made a polarimeter. You have made a polarization-sensitive telescope. Now, you may not be able to immediately know how you would use such a thing, but one way to think about it, now take this guy and look at a light, look at a light source, put one up to your eye, and now put the other one in front of it, anywhere, and now rotate them. What happens to the light source?
Becomes brighter and dimmer and brighter and dimmer.
Yeah. So it's called a quadrupolar pattern, right? So it's repeating. It goes bright, dim, bright, dim. It rotates twice in intensity for every single physical rotation.
Wow.
And that's because of the property of the photon. The photon is a spin one field, but the polarization of light it's the axis at which its electric field is oscillating. Its electric field is marching straight up and straight down. And so therefore vertical polarization is the same as negative vertical polarization. And so you get the same pattern as you rotate 2 times for every one physical rotation. So it's like a spin 2 object. So now if you put that in front of the telescope, you can do one of 2 things. Now you're polarizing all the light that's going in because you have one of the polarizers. And then you can analyze it as you rotate the other one. You can analyze it and change the amount of polarization. Or you can put this kind of very special crystal in here. There's a crystal. It's called calcite. This is from Lex Luthor, not Lex Fridman. This crystal, put it on top of your printed notes there and tell me, what does it look like?
There's I could see everything twice.
It's a double image.
It's a double image.
That is a special crystal that has 2 different indices of refraction. So light emerging, which is unpolarized from the black ink, comes out. And it splits into 2 different directions. And it could split even more if I made the crystal, give you my more expensive crystal, but that's all I have.
What is the crystal with this kind of property called?
It's called calcite. This is crystal. It's called birefringent crystal. Bi means 2, refringent means refracting. So this is a special type of material that separates light based on its polarization.
Pretty clean bi signal.
Yeah.
It's cleanly 2.
Yeah.
I'm seeing 2 very cleanly.
It's very crisp, right? So that's yours to keep with every time you host me. Now, take the polarizer underneath your left hand.
Yep.
Put it on top of the crystal and kind of move it back and forth.
Wow.
What's happening?
This is incredible. You can switch as you rotate, you switch from one signal to the other. So one of the refractions to the other. Whoa.
So that is now you are analyzing the polarization. You are confirming the light comes out of the crystal, 2 different types of polarization. And effectively what we do is we have those two things, if you like, but working in the microwave. So our detector, that's where the cosmic photons are brightest, in the microwave regime of the electromagnetic spectrum. And we're coupling that to a refracting telescope. But your eyes are refracting telescopes. So you are a polarimeter right now. The human eye can actually slightly detect polarization, but otherwise it mainly detects its intensity of light and the color. That's what we call color and intensity, brightness.
So you're devising an instrument that's very precisely measuring that polarization.
Exactly. And doing so in the microwave region with detectors not made of biological human eye retina cells, but of superconductors and things called bolometers. And this has to be done at temperatures close to absolute zero under vacuum conditions, 1/1000th of the pressure we feel here at sea level.
So why is it that this kind of device could win a Nobel Prize?
So when the CMB was discovered, it was discovered serendipitously. There were two radio astronomers working at the time at Bell Laboratories. Now, why would Bell Laboratories be employing radio astronomers? Bell Laboratories was kind of like Apple, or, it was like a think tank, or, it was Google. Let's say it was like Google. Google has like Google X, it has this thing and that thing, right? So they were working there, but imagine if Google was employing radio astronomers, like they were actively recruiting. Why would they do that? Well, it turns out that was the beginning. In the 1960s was the first commercial satellite launch for communication. And so Bell Labs, which would later become the telephone, part of AT&T and the early telephone company, would later invent the first cell phone, the year I was born. And they would take that, 1946, and they would take that telescope technology that radio astronomers had developed, and they would use that to see if they could improve the signal to noise of the satellites that they were seeing. And they found they couldn't. They found that they could not improve the signal noise ratio of the first telecommunications satellite. It was like the equivalent to 1 kilobit per second modem. And they were bouncing signals from the West Coast up to the satellite, bouncing it down, landing it in New Jersey, of all places, in northern New Jersey, Holmdel, New Jersey. And these radio astronomers couldn't get rid of the signal. So they said, well, New Jersey's not far from New York. Let's see if the signal's coming from New York. No, not coming from New York. Let's see if it changes with the year. Maybe it's coming from the galaxy, which was also discovered there by Jansky in 1930 something.
So in the not being able to reduce the signal or increase the signal to noise ratio, the noise was
the noise. They knew the signal was right. They couldn't get rid of the noise, and there was excess noise over the model that had not only been predicted by them, but had been measured by a previous guy, a guy by the name of Edward Ohm. He measured the same signal, found that there was this hiss of static, of radio static that he could not get rid of, that had a value of about 3 Kelvin. So you can translate. Remember I said, if you take a radio telescope and you have pointed at an object that's hot, the radio telescope's detector will get to the same temperature as the object. Mm-hmm. It's a principle of radio thermodynamics. So it's a really interesting thing. It's a thermometer. You can stick it into Jupiter from here on Earth. It's amazing. And so we in radio astronomy characterize our signal not by its intensity, but by its temperature. So he found, this guy, Edward Ohm, there's this 3 Kelvin signal. I can't get rid of it. It must be I did my error analysis wrong. And I would give him an F if he was one of my first year students. But he just attributed it to lack of understanding. These other guys, Penzias and Wilson, who are also radio astronomers, they said, no, let's build another experiment, put that inside of our telescope, and do what's called calibration. Inject a known source of signal every second that has a temperature of about 4 Kelvin, because the signal that they were trying to get rid of is about 3 Kelvin, and you want to have it as close as possible to the pernicious signal as possible. They did that once a second, so they got billions of measurements, millions of measurements over the course of several months, years, and even by the end, maybe millions of measurements for sure. And they found they couldn't get rid of it either, but they measured it was exactly 2.7265 degrees Kelvin.
So how does having a 4 Kelvin source, how does the calibration work, just out of curiosity?
It could be larger. Imagine like you're trying to calibrate the microphone. Like you could do it with like a really loud sound, but the gain would start to compress. So there are amplifiers downstream from the detector in every experiment that I've ever worked on, and they only have a linear region over a very small region, and you want to keep it as linear as possible. That means if you're trying to compare like a voice and you're trying to compare that to a jet engine, it's not going to be as easy on the amplifiers as getting, a slightly loud, a gong or something, a violin.
So the idea if the noise is present in both?
There's noise present in both, and you measure. What they did is they made a separate measurement just of the calibration system, which they measured exactly very well. 4 Kelvin is the temperature of liquid helium. That's a temperature that's not going to change, and it's certainly not going to change over a time scale of 1 second. And so they could compare unknown signal, known signal, unknown signal, known signal, like a scale, like a balance. So another way to think about it is like this. You've seen these Libra kind of balances where you put 2 weights in a pan, right? What happens if you put like a 1 ounce weight on one side and a 20 kilogram weight? You don't get any measurement, right? But you do get kind of a measurement if they're close in weight. That's why they use 4 Kelvin.
Got it. But just to linger on the fact that there's a romantic element to the fact that you're arriving at the same temperature. That's kind of fascinating. And you're measuring stuff you're measuring signal in terms of temperature at the source.
Yeah.
So you get to, there's something about temperature that's intimate.
Yeah.
It's cool.
Yeah. Especially since, all life is basically, conversion of energy and trying to control entropy, which is then related to thermodynamics exactly in that way. And this is very crucial kind of thing to do in science because they weren't looking for the signal. They found it accidentally, these 2 scientists, Penzias and Wilson. And I like to think that those kind of discoveries are the purest in science. Like when you see something, Isaac Asimov once said, like the most important reaction as a scientist is not eureka, which means in Greek, as you know, I have found it. He said, like, that's weird. Like that's a much better reaction, or that's freaking cool. Like that's a scientist. Not like, oh, I found one. Because
surprise.
Yeah. Because if you find what you're going to find, that's what leads us susceptible to confirmation bias, which is deadly. And so, it's close to deadly as possible.
So how does that take us to something that's potentially worthy of a Nobel Prize?
So Penzias and Wilson weren't looking for a signal. They ended up discovering the heat left over from the fusion of helium from hydrogen, et cetera. And that was a serendipitous discovery. They won the Nobel Prize in 1978. It was the first one ever awarded in cosmology. My reasoning is, what if you could explain not only how the elements got formed, but how the whole universe got formed and kill off every other model of science? So if that weren't enough, every scientist, worth his or her salt had told me and Andrew Lang and our colleagues, this is a slam dunk Nobel Prize, if you could do it. Because it was really explaining, again, the stakes of this science is different than like superfluidity, plasma physics. When you talk about the origin of the universe, it ties into everything. It ties into philosophy, theology. You realize if Paul Steinhardt is correct, that the Bible can't be correct. In other words, the Bible is correct now, isn't falsified, if you believe it. I never use the Bible as a science book, obviously. But the Bible speaks of a singular beginning. What if you knew for sure the universe was not singular? It would be more like the cosmology of Akhenaten and Egyptians than the biblical Torah, Old Testament, if you will, narrative. So in my mind, the stakes could not be higher. And again, it's not an offense because we need plasma physics. We need every type of physics except maybe biophysics. Like we literally use every branch of physics, thermodynamics, superconductivity, quantum mechanics, all that goes into our understanding of the instrument. And even further, if you want to understand the theory that predicts the signal that we purport to measure. So I rationalized that if Penzias and Wilson won the Nobel Prize for this, if Hulse and Taylor won the Nobel Prize for indirectly detecting gravitational waves, this is decades before LIGO, by me detecting gravitational waves indirectly, detecting how the universe began, detecting the origin of the initial conditions for the Big Bang nucleosynthesis, which won the Nobel Prize in 1983. These are like 5 Nobel Prizes, potentially. For that reason, it seemed as close as you could possibly get to being a slam dunk, to outdo what my father did, to do, really this impossible. And at that time, Lex, again, it sounds weird because people are like, oh, you wouldn't, you don't really, you still want the Nobel Prize. You're still like greedy. And look, you wrote another book about, and I always joke, I'm like, well, if you want to see if I'm a hypocrite, just get them to give me the Nobel Prize in literature. And if I accept it, then I'm a hypocrite. But,
we'll get to your current feelings on the Nobel Prize in terms of hypocrite and so on.
Yeah.
But so there's this ambition. Let's say this device, this kind of signal could unlock many of the mysteries about the early universe.
Yeah.
And so there's excitement there. So let's take it then further. There's a human story here of a bit of heartbreak. Not only was this possibly worth a Nobel Prize, if the Nobel Prize was given, you were excluded from the list of 3 that would get the Nobel Prize. So why were you excluded? Maybe that's a place to tell the story of BICEP 2.
Yeah, so BICEP 2, like, iPhones, or I know you're an Android fanboy, but, every year they get a little bit better. They get more megapixels, they get more optics, triple X zoom, whatever. Okay, right? We upgraded our detectors as well. The initial detectors were based on what are called semiconductors. They have certain properties that make them very difficult to replicate at scale. And we wanted to make them into superconductors, which had a virtue that you could then mass produce them. Why superconductors? Well, again, we're measuring heat. So one thing about a superconductor is that it transitions from some finite resistance to zero resistance over a very short span of temperature range. That means you can use that very short span dependency as an accurate and sensitive and precise thermometer. And so my brilliant colleagues around the world, in this case, Jamie Bach and nowadays Suzanne Staggs at Princeton, they are just exquisitely making these sensors, tens of thousands of them. The initial BICEP 1 instrument, of course, we just called it BICEP, that only had 98 detectors. Simon's Observatory is going to have 100 times more just in one of our 4 telescopes. We're going to have 60,000 detectors operating full-time at 0.1 degree above absolute zero in the Atacama Desert. We'll get there. But in the case of getting back to what BICEP did, we upgraded it, made BICEP 2. In January 2010, we had just installed in the exact same location at the South Pole, in the same building, which is ominously called the Dark Sector Laboratory, DSL, still operating to this very day. We installed a new receiver on the same platform as before. It had very similar, identical optics, cryogenics, vacuum, everything, except it went from 98 detectors to 512 detectors. So almost an order of magnitude, very substantial upgrade. And it had certain other features that made it even more powerful, but than just a naive factor of 5. And then we started observing with that, and we knew we'd have years to go, and maybe we'd never see anything. Again, we're looking for these tiny little reverberations in the fabric of space-time produced close to the origin of the universe as we could ever get to. So I was playing a role in that. Obviously, it had upgraded my a version of the original idea that I had for BICEP along with Andrew Lang. And in January of 2010, I was at a meeting at UC Berkeley. And I got a call from Andrew Lang's, or I was in a meeting with Andrew Lang's thesis advisor, Paul Richards at UC Berkeley. And he said that Andrew was dead. He had taken his life by suicide. And this is a man, and I'd already lost my father at this point in 2010, but he was like a father figure to me, Andrew. He would give me advice on marriage, on like how I should be with my kids, and what was the most important way to move through the academic ladder. Again, he was preternaturally suited to win the Nobel Prize. Everyone always thought he would win it. He still, if he were alive, he still could win it. In fact, his wife or his ex-wife won it, Frances Arnold, in 2018. And, it's just power couple. And it destroyed me for a long time because, he was just this magical person. I mean, I couldn't conceive of my career, my life, even like, these aspects of raising kids and being married without him. And to do it in that way, it felt like, again, I'm not, he's got kids and I feel terrible for them, obviously, but it did feel like a betrayal. I mean, I'm just being honest with you. It felt like, why the F did you not reach out? I thought we were close and I couldn't, I told him everything and I felt like he had told me everything. And now he was gone. And then inevitably we had to keep running the instrument. I mean, there's millions of dollars invested, careers at stake, young people working tremendously hard. And then here we were. And like, who's going to take over the lead? He was the lead of the project at Caltech. And then it turned out that the other collaborators with whom I had been working for years and shared a lot of ups and downs with as well, they had decided to form a collaboration in which I was no longer the principal investigator. I was no longer one of the co-principal investigators as I was on BICEP 1. So I continued on BICEP 1 as the co-leader of it, but not on BICEP 2. And, obviously that was pretty painful.
This is all happening at the same time as you lose this father figure. Now there's this kind of this one betrayal in a way, and then there's another or something that feels like a betrayal.
Yeah. And he had, kind of been the only one looking out for my interest in the new experiment. I had moved from Caltech to UC San Diego, and there were other postdocs in the mix, all of whom would come there to work with him to get the, the approbation that would then lead to their careers taking off as it did for mine. And so there was a competition. I mean, science is not free from egos and competition and desires, rightfully or wrongfully, for credit and attribution.
Was he the source of strength and confidence for you as a scientist, as a man? I mean, we're kind of alone in this world. As when you take on difficult things, we often kind of grasp at a few folks that give us strength.
Yeah.
Was he basically your only source of strength in this whole journey? Like primarily in terms of like this close-knit?
As a scientist, there were really two. There was one, this Russian cosmologist, Alexander Polnareff, who thankfully is very much alive. It was at Queen Mary University. Now he's retired. He was kind of the theoretical, cosmological father to me. And then Andrew was this counterpoint that was teaching me, you need to have a brand as a scientist. Every scientist has a brand, and some of them don't protect it. Some of them don't burnish it. But some of the skills about being a scientist we don't teach our students involve how do you cultivate a scientific persona? And he was the exemplar for that. In addition to being the avuncular, father figure type character that really, was the person I would talk to. I had issues with my own students, and he would tell me how those were. And he would tell me, his misgivings about, about people that he worked with or things in his personal life. And it was devastating. But again, like, who the hell am I? I'm not his kid. His kids lost father. So I feel guilty talking about it in that sense, but it's just a reality,
Well, there is something that's not often talked about is people who collaborate on scientific efforts. I mean, I don't want to compare, but it's sometimes when the collaborations are truly great, it sounds similar as when veterans talk about their time serving together. There's a bond that's formed. So like comparing family and this kind of thing is, it is not productive, but the depth of the bond is nevertheless real, because you're taking on something, you're taking on the impossible. You're trying to achieve something, sort of like there's this darkness, this fog of mystery that we're all surrounded by, which is what the human condition is. And you are like grasping at hope through the tools of science. And you're doing that together with like a confidence you probably should not have.
Yeah.
But you're boldly pushing through. And then for him to take his own life, can I ask you about this kind of moment that combined, I don't want to say betrayal, but perhaps the feeling of betrayal that BICEP 2 kind of goes on without you, even though you're part of it, you're not part of the leadership group. Can you describe those low points? Was there depression? Or was there a crumbling of confidence?
Yeah, I mean, it was so wrapped up with my identity as a person, like there's only a few different ways to have identity, and unless you're unhealthy psychologically. One of them for scientists is often that they're a scientist, and that sometimes is their primary identity. Now I've got other, I'm a husband and father, but at that time that was my identity. So to have that kind of taken away, it reminded me of being kind of adopted in a sense, like the one who created me, or that I had played a role in my life, that he abandoned me in the sense. It felt like these people are abandoning me. And the only thing I'd correct about the analogy that you use is like in the war, they're all working, for a common good. It's not like I want to get the most kills, or I compare it more to like a band. Like think about the Beatles, and what they did. And then they they ripped apart because of egos, credit. They had solo careers. They had, relations with their intimates and so forth. And there it's not only for the common good. There is more of a zero-sum aspect. Like I always say, science is an infinite game. You can't win science. You never get to we won science. And even the Nobel Prize, they don't feel like, we're done. They feel like a lot of times they're imposters, even to that day. However, science is made up of a lot of finite games where there is only one winner for tenure. There is only only three winners for the Nobel Prize. And because of that, I think it's heterodox and it's very confusing, especially there's no guide. I never got a guide how to be a professor, how to teach, how to lead a research group, how to deal with the death of an advisor, how to deal with an unruly graduate student or two. you know, so we're all like reinventing it, which is kind of ironic and insane if you think about it, because the academic system that I am a part of and you are a part of is 1,000 years old. Dates back to Bologna, Northern Italy, 1088 or so. First universities were established. And, very little has changed. There's some guy or gal scratching a rock on another piece of rock and, lecturing in front. And there's only one better aspect nowadays is that back then, the students could go on strike if they didn't like the professor, and then he or she wouldn't get paid. Probably mostly it was he's back then. Nowadays, that barbaric process has been replaced by tenure. So, okay. But no, it was a definite kind of feeling of the rug getting pulled out from underneath me because he was like my consigliere. He was a guy I, sought counsel and counseled me, and he's dead. And I felt like there is no one who's going to honor the agreements that we had. And he was a very soulful person. He was so much better at being a scientist than I could ever be. And just a loss for the cosmos. It just really hurt. And, I thought, it's so sad because he could have won the Nobel Prize. I don't think like that anymore. First, I think about his kids. Felt at first, now there goes my chance at winning a Nobel Prize. And hence the title of the book was like, I knew I would not win the Nobel Prize. It also means that there's parts of the Nobel Prize that have to be done away with. It's a double entendre. Like we need to lose aspects of the Nobel Prize to help science out. We can talk about that a different time. But in the context of like now thinking back on it, that was such a minuscule part of it because let's say he did win the Nobel Prize or I did win or any of us did. Would that have changed anything? Would that have brought anything back? It's so, we say it's like vanity, it's futility. And I just, for me, the Nobel Prize is like, I don't want to say it's like insignificant because obviously it has a lot of power and it has influence. And, I went back, I had Neil deGrasse Tyson on my show. I'm going to name drop. Okay. And he prepares like a surgeon before doing surgery when he goes on a talk show. So you see him going on Colbert Report. You think, they just have a banter. He's just naturally gifted. No, he said, no. You say that you're undermining what he does. What he does is he goes back, he watches the last month of Colbert Reports or whatever it's called, Late Show. And he says, how long does Stephen pause between questions? How long in the news cycle does he go back? What topics has he talked about with people similar to me? So I took Neil and I did that for you. And I look back, how many times has Lex mentioned the words Nobel and Prize? And I put it into Google Ngram and out came exactly the same number of times as show episodes as of this moment. So you've said the words Nobel Prize over 240 times.
Yeah, I mean, it is so strange as a symbol that kind of unites this whole scientific journey, right? Like, it's both sad and beautiful that a little prize, like a little award, a medal, a little plaque, they'll be most likely forgotten by history completely. Some silly list. It's somehow a catalyst for greatness. It resulted in you doing your life's work.
Yeah.
The dream of it.
Would I have done it without the Nobel Prize? I can't necessarily counterfactually state that would have happened. So no, it definitely has a place. And for me, it is valuable to think about it. But the level of obsession that academics have about it is really, I think it is almost unbalanced, becoming unhealthy. And again, I make no truck with the winners of the Nobel Prize. Obviously, now I've had 11 on the show. And to think about, like the one rule. So by the way, right after the denouement of the story, which I'll get to in a bit, how our dreams went down to dust and ashes. I was asked by the Royal Swedish Academy of Sciences to nominate the winners of the 2015 Nobel Prize in Physics. So like the one that I theoretically could have been eligible to win in 2016, actually, they asked me to nominate. Now imagine if I ask you, Lex, you say, Brian, instead of me inviting myself on the show, if you say, Brian, would you like to come on the Lex Fridman podcast? I say, you know what, Lex, you know that guy Rogan? I think you might have. Can you introduce him to me? You know, like you imagine how that would feel. Like you'd be like, after that, you know, I'm humiliated. So I was asked to nominate the winners, and the one rule that they say of all the rules that Alfred Nobel stipulated, there's only one rule that they maintained. In other words, he said one person can win it for something they discovered in the preceding year that had the greatest benefit to mankind, made the world better, right? None of that was mentioned in the letter. It said many people can win it for work done long ago. They didn't mention anything in the letter to me, signed by the Secretary General, nothing about benefiting mankind. They said just one thing, can't nominate yourself. So none of these guys nominated themselves.
Actually, a little known fact, they sent that exact letter just to you. That rule was created just for you.
That's called the Keating correlate. Yes, exactly.
Just to like
good for them.
Rub it in. It's in this particular case, of course, there's like some weird technicality or whatever, but in this particular case, it's kind of a powerful reminder.
Yeah.
That the Nobel Prize leaves a lot of people behind.
Yeah.
There's stories behind all of that.
Yeah. I mean, here's a good example. Again, this is my friend, Barry Barish. He's become like a mentor and a friend. He wrote the foreword to this, my book, Into the Impossible. He won the Nobel Prize because a different guy died. And he admits it. And he said it. And actually, it's funny with him because I've heard you talk, you know, very rhapsodically and lovingly and romantically about with Harry Cliff and a wonderful podcast with him, by the way, about the LHC and how wonderful it is, and how in that, you know, we were about to build the superconducting super collider right here in Texas, and it didn't get built and it got canceled by Congress and blah, blah, blah. And I say to Barry, that was the best thing that ever happened to you. And he's like, "What the hell are you talking about?" I'm like, "If that didn't get canceled, first of all, the even though it did get canceled, the Europeans went on to build it themselves, saved the American taxpayers billions of dollars, and we wouldn't have learned anything really substantially new, as proven by the fact that, as you and Harry talked about, nothing besides the Higgs particle of great note has come out. And actually, he's had a recent paper, but it's been an upper limit, along with his collaborators, an LHCb experiment that I'm going to be talking with him about. But the bottom line is, it was really built to detect the Higgs. So the SSC, for twice as much money, would have sucked up Barry's career, and he would have been working on that, maybe not. And then he would never have worked on LIGO, and then he wouldn't have won the Nobel Prize, right? So you look at counterfactual history. That's not actually a big stretch, right? If the SSC had still gone on, he would have worked on it because he was one of the primary leaders of that experiment. Second thing, if, imagine the following thing had happened. They won the Nobel Prize because in September 2015, they detected unequivocal evidence for the in-spiral collision of two massive black holes, each about 30 times the mass of the sun, leaving behind an object that had just less than 60 solar masses behind. So one solar mass worth of matter got converted to pure gravitational energy. No light was seen by them. This particular date, September 14th, 2015. Okay. That explosion, because of the miracle of time travel that telescopes afford us, that actually took place 1.2 billion years ago in a galaxy far, far away. They actually don't know which galaxy it took place in still, and they never will. Okay. If that collision between these two things, which have probably been orbiting each other for maybe 1 million years or more, if that had occurred 15 days earlier, Barry wouldn't have won the Nobel Prize. Because
it's hilarious to think that there's one human that won the Nobel Prize because two giant things collided.
200 million years ago. And if it had happened 18 days, 20 days, 30 days, because that was the deadline for the Nobel Prize to be announced, they announced the findings in February, but you have to nominate the winners in January. So I could have nominated them up until January 30th, but they didn't announce anything, and there were just rumors. And so but the reason that he wouldn't have won it, because there was another guy who was still alive, considered to be the founder and father of the three fathers, Ray Weiss, who did win it, Kip Thorne, who did win it, and the third gentleman at Caltech named Ron Drever, who passed away. Again, he was alive in 2016. He died in the middle of 2017, and then he wasn't awarded the Nobel Prize.
And here we are, several billion of hairless apes that strangely wear clothing, celebrated 3 other clothed hairless apes with a medal, with one particular element. And then they made speeches in a particular language that evolved.
Bent down to get those medals in front of another guy
Yeah.
who wears even fancier clothes, who is the king of Sweden. And
then they got some free food
they
afterwards.
get some reindeer meat. That's right.
Okay, excellent. Since you mentioned Joe Rogan in that little example, what happened to you in terms of BICEP 2? I want to kind of speak at a high level about a particular thing I observed. So I was a fan of Joe Rogan since he started the podcast. I just listening to the podcast. I'm a huge fan of podcasts in general.
Yeah.
And it also coincided with my entry into grad school and this whole journey of academia. So grad school, getting my PhD, then going to MIT, and then Google, and then just looking at this whole world of research. What I really loved about how Joe Rogan approaches the world is that he celebrates others. Like he promotes them. He gets like genuinely, and I now know this from just being a friend privately, he genuinely gets excited by the success of others. And the contrast of that to how folks in academia often behave was always really disappointing to me.
Yeah.
Because the natural, just on a basic human level, there is an excitement, but the nature of that excitement is more like, I'm happy for my friend, but I'm really jealous and I want to even outdo them. I want to celebrate them, but I want to do even better. So that's even for friends.
Yeah.
So there's not a genuine, pure excitement for others. And then couple that with just you now as a host of a popular podcast know this feeling, which is like, there's not even a willingness to celebrate publicly the awesomeness of others. People in academia are often best equipped technically in terms of language to celebrate others. They understand the beauty, like the full richness of why the cool idea is as cool as it is, and they're in the best position to celebrate it. And yet there's a feeling that if I celebrate others, they might end up on the cover of Nature or whatever, and not me.
Game, right?
It's they turn it into a zero-sum game. The reason why I think Rogan has been an inspiration to me and many others is that it doesn't have to be that way.
Yeah.
And forget money and all those kinds of things. That I think there's a narrative told that academics are this way because there's a limited amount of money, and so they're fighting for this. I don't think that's the reason it's happening this way. I think you can have a limited amount of money. The battle for money happens in the space of proposal. There's networking. There's private stuff. Public celebration of others and just how you feel in the privacy of your own heart is not have to do anything with money. It has to do with you having a big ego, not humbling yourself to the beauty of the journey that we're all on. And there's folks like Joe Rogan, who in the comedian circles is also rare, but he inspired all these other comedians to realize, you know what? It's great to celebrate each other. We're promoting each other, and therefore the pie grows.
Yeah.
Because everybody else gets excited about this whole thing, and the pie grows. Right now, the scientists, by fighting, by not celebrating each other, are not growing the pie. And now, because of that, sort of science becomes less and less popular.
It's a flywheel. And exactly. No, and I want to point out two things. One is that I remember you went on Joe's show maybe a couple of years ago, and then he gave you a watch. He gave you like a Rolex, right?
Yeah.
And I tweeted to you, and I think
Omega.
Omega. Sorry. Okay, fine. The watch that went to the moon, which we will get to in a bit. I don't think he could give you what I gave you, though. By the way, and we'll get to what that final gift package is for you.
And by the way, I also wanted to mention, because when you said Joe Rogan, I would not be upset, and you should definitely go on Joe Rogan. And we had this conversation with him.
Yeah.
Because I was like, when I was so moving to Austin, and had a conversation like, don't you think it's weird, like if we have the same guests at the same time or whatever? He's like, fuck that.
Yeah.
I want you to be more successful than me. He truly wants everybody, like especially people close to him, to be more successful. Like there's not even a thought like.
But you know why he does. And this is what I tweeted to you, and one of the few things I think you have retweeted that I sent you. I said, someday you're going to give that to somebody. And today I wanted that to be me. No. Joe's Omega. No, but the point is, he sees in you that same, grandiosity, that same genuine spirit, graciousness. And I think that's true. I mean, you do something very rare. I don't want to turn this into too much of a love fest, but I do want to say, even back to Andrew, who I've almost been hagiographic about, just treating him like a saint. He said to me the same thing when, in a moment of peak, said like, God damn it. Like, I have to train these guys and women that work for me so that they can be better than me, so that they can go out and compete with me for the same limited amount of funding from the effing NSF. That wasn't who he was. That was just an expression. Like, I'm doing something which is fundamentally, but you know what? When you have kids, hopefully, please God, you will someday. Because I think, and I hope we can get to talk about that later, but part of investment and part of doing something with, when you have a kid, like, you can get married. You can marry someone because she's rich or he's rich, or you can marry someone because they're good looking or he's good looking. You can marry for all these different reasons that are ultimately selfish. There's no way you can have a kid and be selfish. Nobody says like, oh, you know what? I really want this thing that's 3 feet tall, that doesn't speak English, that craps on my floor, that wakes me up all hours of the night, that interferes with my love life. Nobody says that because it doesn't benefit you for months and months. A friend of mine who actually does the videos for me and does a lot of my solo videos, he's having his first kid. He's like, what do I do? Because he always gets stupid advice. I'll catch up on sleep now. Like, yeah, I'm going to store sleep in my sleep bank. Like, I don't think Huberman and you talked about that, right? You can't do that. That's stupid. What you can do, give the kid a bath. Feed the baby, let the mother relax. Like, in other words, do the things. And this really relates back to what Aristotle once said. Aristotle once said, why do parents love kids more than kids love parents? As much as you love your dad and your mom, they still love you more. And because you love that which you sacrifice for. Here's a proof. I know a lot of families that have kids with special needs. Some with severe, one of my uncles, on the Keating side, had severe, what they called mental retardation. Now it's probably has a different name. That, out of the 9 other brothers and sisters, he was their favorite because they had to sacrifice so much for him. And I think of that, in the small case, like Joe's kind of mentoring you or whatever, and you're going to mentor someone else. You love that which you sacrifice for. Sacrifice is reduction of entropy. It's storing and investing, and you want to protect that. And, that to me really speaks to this. So, I don't hold it against, but it is true. Like, scientists are, when they're described, again, they're often said to be like children, right? You've heard this description. They're inquisitive, they're curious, they're passionate, they love it. And I'm like, yeah, and they don't play well with others. They're jealous, they're petty, they're selfish, they won't share their ball and they go home. Yeah. You can't, there's no such thing as a single-edged sword. I wish there were, because we need some more of that because you got to dull it up. But in this case, I think when you have this kind of investment in science, it's going to be natural. But that doesn't mean we have to feed the flames of competition. I'm like really if you go to the homepage of the NSF or the Department of Energy or the recently released National Academy of Sciences Future of Science for the astronomical sciences for the next 25 years or more, they talk about how many Nobel Prizes these different science things could win. Exoplanets, life, the discovery of the CMB, B-mode polarization, the nice study, that's figured too in this thing. And I'm like, what message is that sent to kids? Like, to young people? Like, that's what you should be doing so that you win this small, as you said, this prize given out by one hairless ape to another wearing a fancier costume, eating reindeer.
In the case of Nobel Prize, it's only currently given to 3 people.
At most, which was never one of his stipulations. He actually said 1. You can only give it to 1 person. So they change it. Why did they change it? I speculate in the book. By the way, the book's only 3 chapters out of 11 about the Nobel Prize and its effect. But, one of the things that's been so interesting, like I'm speaking, actually this coming up in December is the Nobel Prize is given out on the day of Alfred Nobel's death. There's a lot of, and they bring in flowers, not from his birthplace, but from his mausoleum, which is in San Marino in Italy. It's a lot of like death fascination. Denial of death features heavily in the Nobel Prize because it's like, what outlives a person? Well, science can outlive a person. My father has a theorem named after him. It's still, engraved in many places around the world. You or I, we can go to different places around the world. People know who we are based on our publications. We engrave things. We want to store things. We want to compress things. And I think there's something beautiful about that. But there is a notion of denial of death. Like, there is a notion of what will outlast me. Especially if you're among the many 90-something% of members of the National Academy don't believe in an active faith, in a creator, in a God, and science can substitute for that, but it's not ultimately as fulfilling. I don't believe it can fulfill a person the way even practicing but not believing in a religion can fulfill a person.
So, which is interesting because you do bring up Ernest Becker and the denial of death in losing the Nobel Prize book. And there is a sense in which that's probably in part at the core of this, especially later dream of the Nobel Prize or a prize or recognition. I've interacted with a few, or a large number of scientists that are getting up in age. And there is the feeling of real pride, of happiness in them from winning awards and getting certain recognitions.
Yeah.
And I probably at the core of that is a kind of immortality or a kind of desire for immortality. And that was always off-putting to me, as opposed to, I mean, I know it sounds weird to say it's off-putting, but it just, rather than celebrating the pure joy of solving the puzzles of the mysteries all around us, just the actual exploration of the mysterious
for its own sake.
For its own sake.
Yeah. Well, that's why I said, it's like a scientist should, you have to be careful and not have any, physical, it has to be platonic, but you can think of scientists and mentor. I have a chart in the book and in a plaque made by one of my graduate students, former graduate students. She's now a professor in New Mexico, Darcy Barron. And she made this plaque and it has 17 generations. So here I am, 17, levels down. There's a guy, Leibniz, not the famous Leibniz, different Leibniz, 1596 he was born. And I'm in this chain. And I don't know if you know this, but in the Russian language, the word scientist means someone who was taught. I'll say it very slowly. One who was taught, right?
Uchone.
So it probably means like a guy who was taught, right?
No.
It could just mean a person.
No, it's literally someone who was taught.
Someone who was taught, right.
Yeah.
So what does that mean? To me, it has a dual kind of meaning, at least dual meaning. One is that you have to be a good student to be a scientist because you have to learn from somebody else. Two, you have to be a teacher. You have to pay it forward. If you don't, I claim you're really not a scientist in the truest sense. And I feel like with the work that I do in outreach and stuff like that, I'm doing it at scale. I'm influencing more than the 24 kids I might have in my graduate class or undergraduate class. And they're, potentially could reach thousands of people around the world and make them into scientists themselves, because that's the flywheel that is only beneficial. There is no competition. There is no zero-sum fixed mindset versus growth mindset, because it is an infinite game. Imagine a culture that had none of the trappings of the negativity of the Soviet Union or pre-World War I Germany or Imperial Japan. Science celebrated. And we're just making like a nation of scientists, and like we're not doing it to become multi-billionaires or necessarily, for any military purpose whatsoever. But if we had that, sometimes I'm flying, home at night, like when you fly into LA, you literally, it's very rare you can see like the number 10 million. Like it's very hard to like visualize things. That you see a brick wall, you ask how many bricks are there? It might be 1,000, 2,000. 10 million lights. There's 10 million souls. And you can see, and they're discrete. They're not like the Milky Way all blending together.
Each lost in their own busy lives,
right.
Excited, fall in love, afraid of losing their job, all that. By the way, people should know that you're a pilot. Yeah. So you literally mean fly.
Yeah, sometimes I get to do it. Yeah.
You get to look at the eye of God perspective on these 10 million, on these millions of
and I often think they're like constellations, but upside down. Like the city is like a constellation. Hopefully I'll keep the plane the right way up. But when you think about that, like imagine they're all working together, and imagine like you always talk about love, but like you don't know that they're not worthy of love. Like, so you're looking down on them, and it's just amazing because you think like, what an amazing creation is man and humans, and what can we do? It's phenomenal. It's so exciting. And then I get to do it, it's a job I say, don't tell Gavin Newsom, but I do it for free. I love what I do. But to think about like, oh, if my student succeeds, then I'm not, no, it is unfortunate that you have experienced it. I've certainly experienced it. And I think there are ways around it. I think it is a vexing problem because people want to, it's very tempting to keep your own kind of, garden fertilized. One thing that's interesting is like, people are like, why are you doing this thing? And, podcasts, and you're supposed to be a, serious scientist leading this huge project and, collaborators. And I'm like, well, most of what I do, as I said before, it's for you, it's Velcro. For me, it's like, what is the deal with the safety standards on the truck that we're driving up to deliver the diesel fuel that will power the generator that will allow the concrete truck to. It has nothing to do with the Big Bang, inflation, the multiverse, God's existence. It has nothing to do with that, right? So those are people I say I have to talk to. The people that come on the show, those are people I want to talk to. And that's super fun. Yeah. I mean, it's a real honor that I get to do it. I have some unfair advantages, right? I'm at a top university. We have people that's affiliated with the Arthur C. Clarke Foundation, brilliant scientists coming through. But I felt like it would be kind of a shame if I didn't, allow them to teach at scale, because they're better teachers than I am.
Let me ask you a interesting, maybe difficult question. Have you ever considered talking on your podcast with the people who would get the Nobel Prize for BICEP 2 if it turned out to be detecting what it is?
Yeah, I mean, I'm still friends with them, and they have still gone on to. So we should say like why we didn't win the Nobel Prize, and then what happened with the group that is now leading it, completely that I'm completely divorced from in a secular sense. We're friends, we see each other, we send each other emails and stuff like that.
I would love to get their sense of like what the natural heartbreak built into the whole process of the Nobel Prize, what their sense is. I would love to hear an honest, real conversation. I understand you're friends.
Yeah.
Yeah, there's some hard truth that even friends don't talk about.
They weren't happy I wrote the book. I mean, I remember one of them, was like, well, what's this I hear about a book? And I mean, a lot of people told me not to write the book. They said it's going to give, too much attention to the Nobel Prize. It's going to look like sour grapes. Yeah. Again, I say you can prove I have sour grapes or not. Just give me the next prize. No.
If you get a Nobel Prize for literature, you would turn it down?
I don't know. It's funny because Sabina Hassenfelder, who's a fellow kind of YouTube sensation, and
a shoo-in for the Nobel Peace Prize.
You're right. She's so gracious and so good. She has that German, just gentileness.
She's a little too nice for my taste. Yeah, I would say.
I wish she could really say what she thinks and be snarky on occasion. So she wrote a review of my book when it came out 3 or 4 years ago, and she said, well, Brian Keating, like she said, well, it's it's interesting. He talks a lot about cosmology, but they can do whatever the hell they want, and he presumably has this problems with it, but it's none of his business. Basically, it's a private. And at the end, she said, but if you want one good thing, he's a really good writer, and who knows, he could win the Nobel Prize in literature someday. I said, and then she allowed me to publish a rebuttal on her blog, which was kind of funny. But anyway, no. So getting back to the guys that we were, kind of collaborate-enemies or frenemies, and we're still we don't wish each other active ill. I've visited them. They're welcome to visit me. They have visited me. The thing I have to say is that I just wonder about introspection. Like for me, literally, I don't care about the Nobel Prize other than what it can do to, benefit science. But but by the way, I did seriously care about how it benefit Brian Keating early on in my career. I'm just totally honest. I'm not proud of it. It's kind of embarrassing. But now I would hope that people would say like, okay, the guy is like, it's not, he's obsessed with it. My next book is not about this. It's about something completely different. And, I do feel like people, lack introspection a lot of times in science. Like we don't think about why we're doing what we're doing. And I think it comes down to curiosity. One thing about Joe, and again, I've only listened to like, I have to confess, you're like my father. Now I'm confessing my sins. It's you, Father Lex, Father Fridman. I haven't listened to like that many of your episodes start to finish. Okay. With our mutual friend, Eric, I've listened to a bunch of recent ones, Einstein. Weinstein. Weinstein. That's what it is.
I get them confused with the brother.
The brothers Karamazov, the brothers Weinstein, and a few others. I haven't ever listened to a full Joe Rogan episode, but from what I've seen with him, he has a preternatural curiosity. Mm-hmm. He doesn't have passion. There are a lot of podcasts that have passion. Like I've been on their show. He has curiosity. Like he's not going to stop talking about something until he hops it, until he understands it, until he gets it viscerally. And I respect that because, as I say in this more recent book, passion's like kind of like the dopamine hit that gets you started. Like, oh, I'm going to be great. Maybe I could win a Nobel Prize. Like that's not going to sustain you. Mm-hmm. The sustenance comes from the passion converting to curiosity. And what I want to do is convert, as many things as possible to things that I can then, because actually I've had on, people that discuss addiction. And there is an addictive quality to, doing podcasts or whatever, but there's an addictive quality of being a scientist. And you get to do things that are very specialized in specialized locations with special people, paid for by other people who have no freaking idea what you do. I mean, imagine you worked in some job, and Feynman said all these contradictory things. Like when he was once said, like, he said, if you can't explain it to your grandmother, you don't understand it yourself. Mm-hmm. Then the day he won the Nobel Prize, a reporter asked him, "What'd you win it for?" He said, "If I could explain it to you, bud, it wouldn't be worth a Nobel Prize." Yeah. So let's leave aside his inherent contradictions. But in reality, there is that kind of like dopamine rush that you get from it. But what is ultimately going to be the sustenance of it? So yeah, I do feel like we have to find a way to nucleate that. I don't know, actually. I don't know if it's like, can you turn someone into a scientist? I used to ask this question all the time. Like, can you make someone creative? Like, can you teach someone to be creative? I don't know. Can you teach someone to be curious? I don't know. I do know that kids are naturally curious. As they get older, they get less curious. Just like I heard from the other forward authors, James Altucher, he said once they did a study, kids smile 300 times a day, or smile or laugh. Adults 5 or 6. 5 or 6. No, I'm just trying to get you to laugh, but you're not going to. But anyway, no, it's true. So somewhere you lose 30, to 50%.
I'm not entertained. But that's because I'm an adult. No, and then I do remember there's some distribution on those studies with the happier adults smile a little more, but still the kids blow them out of the water.
Just crush it. So in other words, should we invest our energy in getting the half-life decay constant stretched out more for curiosity for kids? Or should we try to reset the dopamine hit and then, I don't know. It's an open question.
Well, I think it goes to David Foster Wallace, the key to life is to be unboreable. I think I think you could train this kind of thing, which is in every single situation. So like, which I think is at the core, at least this correlated with curiosity, is in every situation, try to find the exciting, the fascinating. Like in every situation, you sitting at waiting for something at a DMV or something like that. Find something that excites you, like a thought, like watch people, or start to think about, well, I wonder how many people have to go to the DMV every day. And then try to go into the pothead mode of thinking like, wow, isn't this weird that there's a bunch of people that are having to get a stamp of approval from the government to drive their cars, and then there's millions of cars driving every day.
How can I do this better? Maybe there's some blockchain, and they could like VIN transfer. Yeah, exactly. Yeah. No, that is a good.
And then every situation, I think if you rigorously like just practice that at a young age, I think you can learn to do that. Because like sometimes people like ask me for advice and like what to do this thing or that thing. Is I think you at the core really have to have this muscle of finding the awesomeness in everything. Because if you're able to find the awesomeness in everything, like whatever journey you take, whatever weird
meandering path
that you take through life is going to be productive. It's going to end up in a great place. So like that muscle is at the core of it, and I guess curiosity is central to that. But you didn't win the Nobel Prize. The team of BICEP that led the BICEP 2 didn't win the Nobel Prize because of some space dust.
That's right. Cosmic schmutz.
Which one is the moon? Which one is...
That one's the dust. The space dust, yeah.
What are we looking at? So why is space dust the villain of this whole story?
Well, it's funny, I wrote these books, and I don't know about you, but when you get all these books, I'm sure you get books, people send you books, they always come in these dust jackets, right? I was like, what the hell is a dust jacket? Like, how much dust is raining down at any moment? I mean, this is immaculate. This room is Russian tidiness galore. But in a normal household, how much dust is raining down? It's not really pretty until I wrote a book. And I realized, I'm writing a story about the origin of the universe, and the prologue, to the cosmos, and dust is going to cover this story. It's actually more a story about astrophysics and cosmology than dust. And this is the link between the cosmological and the astrophysical. So what does that mean? So astrophysics is, broadly speaking, the study of physical phenomena manifest in the heavens, astronomical phenomena. Cosmology is concerned with the origin, evolution, composition of the universe as a whole, but it's not really concerned with stars, galaxies, and planets per se, other than how they might help us measure the Hubble constant, the density of the universe, the neutrino content, et cetera, et cetera. So we have a tendency to kind of look a little bit, they're like, not all astronomers and astrophysicists are equal. They're all equal, but some are more equal than others. So we have kind of a prejudice, a little swagger, right? And cosmologists are studying, we're using Einstein, we're not using Boltzmann, or we're thinking of the biggest possible pictures. In so doing, you can actually become blinded to otherwise obvious effects that people, would have not overlooked. In our case, when we sought out the signal, we were using the photons that make up this primordial heat bath that surrounds the universe, luckily only at 3 degrees Kelvin approximately. We're using those as a type of film onto which gravitational waves will reverberate it, make them oscillate preferentially in a polarized way, and then we can use our polarized sunglasses, but in a microwave format, to detect the characteristic twofold symmetry pattern of under rotation. That's the technical way that we undergo it. I mean, there's a lot more to it. But there are more than one thing that can mimic exactly that signal. First of all, when you look at the signal, if inflation took place, big if, but if it took place, the signal would be about 1 or 2 parts per billion of the CMB temperature itself. So a few nanokelvin. The CMB is a few Kelvin. The signal from these B modes would be a few nanokelvin. It's astonishing to think Penzias and Wilson, 1965, measured something that's 1 billion times brighter. And that was 60 years ago? Let's call it 60 years ago since they discovered it. Moore's law, you're more expert than that. Let's call it every 2 years. So you're talking about like 2 to the 30th power, doubling or something like that at that. So let's call it 2 to the 20th, something like that. So that's like only 2 to the 10th is 1,000, right? Correct my math, I'm wrong. Yeah, 2 to the 20th is 1,000,000, right? 2 to the 30th is 1 billion. So we're outpacing Moore's law in terms of the sensitivity of our instruments to detect these feeble signals from the cosmos. And they don't have to deal with, in the semiconductor factory in Santa Clara, California, they don't have to deal with meteorites and and things like coming into the laboratory. It's a clean room. It's pristine. They can control everything about it, right? We can't control the cosmos. And the cosmos is literally littered with particles of schmutz, of failed planets, asteroids, meteoroids, things that didn't coalesce to make either the Earth, the Moon, the planet Jupiter or its moons, or get sucked into them and make craters on them, et cetera, et cetera. The rest of it is falling, and it comes in a power spectrum. There's very few, thank God, Chicxulub-sized, impact or progenitors that will take out all life on Earth. But there's extremely large number of tiny dust particles and microscopic grains, and then there's a fair number of intermediate-sized particles. It turns out this little guy here is the end product of a collapsing star that explodes in what's called a supernova, type 2 supernova. So stars spend most of their life fusing helium nuclei, protons, into and neutrons into helium nuclei, and then from there it can make other things like beryllium and briefly make beryllium and carbon, nitrogen, oxygen, all the way up until it tries to make iron and nickel. Iron and nickel are endothermic. It takes more energy than gets liberated to make an atom of iron. When that happens, there's no longer enough heat supplying pressure to resist the gravitational collapse of the material that was produced earlier. So the star forms, goes inside out. That's how scientists discovered helium was discovered on the sun. I don't know. Did you know? That's why it's called helium. Yeah, they went there at night. And
well done.
They went there at night. No, helium means Helios is the god of the sun. It was discovered in its spectrum from observations of the telescope like 150 years ago. It wasn't discovered like when oxygen and iron was discovered. So it's only a relatively recent comer to the periodic table.
So helium came after oxygen.
Oh no! First hydrogen forms into helium. So that's the first thing that formed.
No, in terms of discoveries.
Oh yeah, after oxygen. Yeah, I think Priestley and others. Dalton discovered it in the 1700s. No, helium was really only discovered from the spectrum of looking at the sun and seeing the weird atomic absorption and called Fraunhofer lines in the solar spectrum. So, but when it tries to make iron, there's no longer any leftover heat. In other words, there's heat left over from fusing, as you know, the son of a plasma physicist. You fuse to hydrogen nuclei, you get excess energy, plus you get helium. So that's why fusion energy could be the energy source of the future, and it always will be. No, hopefully it'll come much sooner than that. And so trying to make iron, it takes more energy, doesn't give off enough energy, star collapses, explodes, and what does it spray out into the cosmic interstellar medium? It sprays out the last thing it made, which is that stuff. Luckily for us, because some of that coalesced and made the core of the Earth, onto which the lighter like silica and carbon and the dirt and the crust of the Earth were formed. And some of that made its way to the crust. The iron made its way to the crust. Some of that your mother ate and synthesized hemoglobin molecules. And hemoglobin has iron particles in it. It's a quite amazing substance. Without it, we wouldn't have our red blood. We wouldn't exist as we are.
Is this a very long, complicated mom joke?
I've done enough dad jokes. My quota's up. So taking this object, seriously, there's not all of it gets bound up in a planet. In fact, forming planets is very inefficient. And so there's a lot of schmutz left over, some of which gets in the way of our telescopes looking back to the beginning of time. And some of those molecules, like iron, is used in compass needles, right? They're magnetized. And magnetic fields in our galaxy can align them and make the exact polarization pattern that we're looking for. As if the compass needles get all aligned, that's like the polarization of the dust grain. It's like that polarizing filter. That means light polarized like this will get absorbed, and light polarized like this will go through. Mm-hmm. So it's making 100% polarized light out of an initially unpolarized light source. Mm-hmm. And that's what happened. And what we ended up claiming on March 17th, and I'm sure if you were there, you might remember this, at the Harvard Center for Astrophysics, there was an announcement. There were like 3 or 4 Nobel Prize winners in the audience. And the BICEP 2 team, which I was no longer leading, I was still a member of it. In fact, in the announcement, the first person they mentioned, besides, thank you all for being here, is me and my team at UC San Diego, although I wasn't invited to go to the press conference because that
Harvard
complicated. Yes, exactly. It's a little school up there in Cambridge area. And so they ended up making this announcement that we had discovered the aftershocks of inflation. We had detected the gravitational waves, shaking up the CMB. And on that day, past Lex Fridman podcast, back when it was called Artificial Intelligence, Max Tegmark said, goodbye, universe, hello, multiverse, and hello, Nobel Prize. So he saw that as confirmatory evidence, not only of inflation, not only of gravitational waves, but of the multiverse. Goodbye, universe. Hello, multiverse.
Multiverse is a natural consequence
of inflation, yes. According to its prominent, supporters. Yeah.
And of course, leave the poetry to Max, which he does masterfully. Yes. Okay. So the excitement was there. Yeah. I mean, maybe the initial heartbreak for you is there too. Yeah. That's some of the darker moments you're going through, but broadly for the space of science, there's excitement there.
Huge excitement. And I often note that this is a problem in what I call, the science media complex, because oftentimes you'll see things like past guest Sarah Seeger, Venus life, exists. And that will be really, it's fascinating, right? And with the work that she's doing or her colleagues are doing, or Clara, who was on your show as well. And that will be on front page, New York Times, Boston Globe, San Diego Union Tribune. It'll be above the fold, make headlines around the world. And then 6 months, 12 months later, as is the case for us, retraction. Page C17 of the Saturday edition that nobody reads, and underneath the personal. So we have a problem in science that if it explodes, it leads, and we get this huge fanfare. And this is not unique to my experiment. This happened with the earlier discovery of so-called Martian life discovered in Antarctica. Which was announced after peer review. We weren't peer reviewed at the point when we made the announcement. We had a press conference, and there are other reasons that the team leaders felt it was important to do that so that we don't get scooped by a referee who's unethical. Yeah. We thought we had done everything right, but that's confirmation bias.
So there's like levels to this.
Yeah, there were many levels. And there were people, me warning about how it would be interpreted and wanting to also make sure that we put all the data out, including the maps, which we still haven't released. And so there were a lot of reasons to be skeptical, but the public never knows this. Yeah. I think so I've made a rule that if I am ever in charge of, doling out large amounts of science funding, that when you should keep kind of an option. In other words, you should have money for publicity. It's fine. Have money for your press conference, but hold in reserve in a bond to be used, hopefully never, but if it's to be used, an equal fund for the retraction, if it should occur.
So you would like to see, because that's a big part of transparency, to me, in the space of science at least, that's as beautiful because it reveals it tells a great story. There's an excitement. There's
Humanity.
So there's a climax to the triumph, but there's also a climax to the disappointment at the end, because that also eventually leads to triumph again. That's the drama that sets up the triumph, like with Andrew Wiles proving Fermat's Fermat's theorem. I guess it's not last name, whatever. The ups and downs of that, the roller coaster, the whole thing should be documented.
That is science. And when we don't do that, then we cultivate this aura that excludes other scientists, often from minorities or women back. That you have to be Einstein. Like Einstein came out of the womb and he was just like this guy with like curly. No, he wasn't. He wasn't bad at math. That's all nonsense. But he said that when he said he attributed his success to, Lex, he said, I never asked my dad what happened when I ran alongside a light beam as a kid. And thank God I didn't, because had I, he would have told me the best answer of the day, which, by the way, he would create 20 years later as a 26-year-old in the patent office, obviously in Switzerland. And in so doing, by delaying when he asked these questions, he said, I approached it with the intellect of a mature scientist, not a little kid. And I wouldn't have accepted the same explanation. So sometimes assuming that scientists are infallible, ineffable, omniscient, I think that really does a disservice. And Jim Gates said, he's like, Einstein wasn't always Einstein. And we cultivate this mystery and allure at our peril because we're humans until we have artificial Einstein, which I don't think will ever exist.
You've launched the assay or project where you hope to assess theories of everything with experiments. You have a YouTube video where you're announcing that. It looks super cool. Mm-hmm. Can you describe this project? And you also mentioned you give a shout out to a little known fellow by the name of Galileo Galilei as an inspiration to this project.
Yeah, so Galileo is kind of my avatar, my hero, the kind of all-around scientist that I would love to approach the logarithm of Galileo. He was not only a phenomenal scientist, he was an incredible artist, a writer, a poet, a philosopher. And back then they didn't have distinctions between scientists and it was like a physician was like a physicist. And he would indulge, kind of these really intellectual flights of fancy, thinking about phenomena such as the Earth's tides or the composition of the Milky Way. And what's interesting about Galileo is that he was almost as wrong often as he was right. And Galileo was not alone like this. I always say, like, Einstein had at least 7 Nobel Prizes that he could have won for discoveries that later became true. But he also had 7, huge, impossible to believe blunders in some sense. It's too bad because he could have had a good career, as I always say. And Galileo was like that too. In other words, he would fall victim to, I think, this confirmation bias that all scientists have to guard their lives against, their careers, their brands, their reputations against, which is the exclusion of evidence that doesn't conform to what you're trying to prove for one reason or another, or the radical acceptance of things that do comport with it in order to bolster your confidence in. And both are equally intoxicating. It's confirmation bias is a hell of a drug because it really reinforces this notion, which is partially sunk cost. You put so much time, effort, money, reputation into it. You don't want to be wrong and go back on it. And with Galileo, he would be incredibly perceptive about things such as the Earth being not located at the center of the solar system and the sun being the center, so-called Copernican hypothesis. And he would use as evidence very, very interesting ideas that all of which were wrong, basically. And in fact, we weren't able to prove that the Earth orbited around the sun. And I ask you, can you prove the Earth is not flat? No. Well, you're a flat earther anyway. But it's. I asked my
proud Flat Earth Society member. T-shirts coming out soon. LexFridman.com /merch.
But it's actually not trivial to do that. But most of my students, graduate students, can prove that the Earth is round or explain how the Earth.
It is actually not trivial to do, though.
It's not.
Yeah.
And much harder is to prove that the Earth goes around the sun. In fact, that's extremely hard to prove. And almost none of my students, even after they get their PhD on the final exam, I kind of like to just, give them a little bit of humility. Because I think to be a good scientist, you need to be humble, you need to have a little humility, and you need to have swagger. You need to feel like a little cocky, like I can do this. I can do this thing that Einstein, by definition, couldn't do. I'm going to attempt it. I'm going to attempt to do what was impossible just a generation ago.
How do you prove that the Earth goes around the sun? So you have to. Is it by the motion of other planets?
So there are many ways to do it. I mean, obviously, you could take a spaceship, park it at the north celestial pole of our solar system, and just watch what happens. But obviously, that wasn't how it was discovered in the late 1700s. So it's called aberration. So if you look at stars as the Earth orbits around the sun, the position of the stars will shift slightly because of the tilt of the Earth, and because the Earth is in motion around the Earth and around the sun, and because the Earth has a non-trivial amount of velocity compared to the speed of light in its orbit around the sun, the stars will trace out little tiny ellipses, and those will correspond to the fact that we're moving around. If they're at infinite distance, which we assume that they are, they're not really, but for all intents and purposes on the scale of the solar system, they're infinitely far away. So that's called stellar aberration. And that was the first way it was discovered. And actually, we still use that. We have to correct for that effect when we measure the cosmic microwave background. Because imagine you're inside of an oven. It has some temperature, 3 Kelvin, 1,000 Kelvin, whatever. If I'm moving towards you, the photons that are coming to me in that direction will be blue shifted, hotter, and the ones behind me will be red shifted. I'll artificially impute a greater or lesser amount of matter or energy where you are, and it's an extension of the Doppler effect. So we actually make use of that and construct what's called like a local standard of rest. Anyway, so you can do it. But Galileo said, no, I'm not going to wait for that. I have other proofs for it. One of which is that the Earth has tides, and the tides come in and out twice a day, high tide and low tide. And he made the analogy of, because the Earth is moving around the sun, say this is the sun here, and it's moving around the sun, but it's also rotating on its axis. See how the water is sloshing up and down inside the vodka bottle? As that happens, he said that's what the tides are caused by. Totally wrong.
Most people listen to this podcast. Just so you know, if you're listening to this, he actually has a bottle of vodka in his hand.
Half drunk.
And we're both drunk and whatever else is possible.
Right. So as it sloshed around, he claimed that was what. Now, it has nothing to do with that. The moon, over there, the moon pulls differentially on the Earth and the Earth's ocean. That causes the oceans to bulge slightly towards and away from where the moon is. And the moon is actually the source of the Earth's tides. It has nothing to do with Copernicus, the orbit of the sun. So he was totally wrong about that. He also thought that the Milky Way was comprised only of stars, when we know it's made of gas, dust, nebulae, and things like that. So he had a fair share of blunders. Now, one thing I always kind of make note of, and I'm actually producing along with Jim Gates, Fabiola Giannati, Frank Wilczek, and Carlo Rovelli, and my friend Lucio Piccirillo, the first ever audiobook of one of Galileo's dialogue, the one where he claimed to find evidence for the orbit of the Earth around the sun, but it was an error.
So you're reading parts of this text,
which is incredible. Brilliant book. So this book was written in 1632. It was written, and it was the one that caused him to go into house arrest and almost threatened to be tortured. And that book laid out his arguments for what was called the Copernican or the non-peripatetic, Aristotelian, etc., notion of the planetary dynamic. And eventually he was forced to recant that he believed in it, and allegedly he said he still believes the Earth moves. Anyway, so we're making that. It's written in the form of a trilogue. It's actually called the dialogue, but it's 3 people. There's one named Salviati, who is espousing Galileo's notions about how the heavens were orchestrated. And Salviati means like the salvation, the savior. Then there's a middleman, Sagredo. So Carlo Rovelli is playing Salviati, the brilliant one. I am playing Sagredo, who's like an intelligent interlocutor. I'm kind of just, I can appreciate Aristotle. I can appreciate Copernicus. Then there's this guy, Simplicio, the simpleton. And he espouses the words of the Pope. So you can imagine, like, you're working in the Putin's government, or you're working in whatever, and all of a sudden you're kind of putting the words of like the fool, literally calling the fool, but you're using the words of the all supreme powerful being on earth at that time, was the Vatican Church, especially for an Italian like Galileo. So he wasn't as brilliant, politically as he was astrophysically and otherwise.
Who's doing Simplicio?
Simplicio is a friend of mine in University of Manchester named Lucio Piccirillo. He's an Irish guy, but he has an Italian. No, he's a full-blooded Italian. But they all speak English and Italian. I only speak. And the forewords are written by. So one foreword in this place has 3 forewords, which is like a 12-word. Okay. The forewords are written.
That joke for me.
Yeah, that was a good one. The foreword, 3 forewords. One of them is written by Albert Einstein, in which he says Galileo was not only one of the greatest scientists in history. This is Einstein telling Galileo, but he was one of the greatest writers and minds of all of human history. That foreword is read by Frank Wilczek, who you've had. Jim Gates, who you've also had. He reads the translation, the translator, Stillman Drake, who's a renowned scientific translator. And then Fabiola Giannati, she reads the introduction and dedication from Galileo to the Duke of Tuscany, and some of the different introductions that Galileo himself had. It's such a thrill to be able to do it. And I only randomly found out because I wanted to study it, and it's like 500 pages long. And I was like, let me get the audiobook because I'm an audio medium kind of guy. Didn't exist. So I said, let's do it ourselves. And so we did it. And hopefully it'll be out on Galileo's birthday, which is February 15th, 2022. It'll be a ripe 457. But that's not the only one of his books. Galileo wrote many books, one of which is called The Military Compass. And this is an interesting book for my blockchain and your blockchain aficionados. In this book, he talks about a compass, which is not a magnetic compass, but an actual like slide rule. It's basically a slide rule. And it's a manual. It's like, imagine if your phone, came with a manual. Nowadays they don't, right? But this was a manual for how to use this slide rule, which is like enormously important. And he gives a whole bunch of worked examples. It's a brilliant book. One of the examples is how do you convert money? So he does a currency conversion between Ducati and Florentine Ducati and Scuti and whatever, lira, whatever. He does all these currency conversions. One copy of this book, or maybe 2 exist, first printings from 1600 still exist. If Galileo had just kept those in his family, they're worth $100 million. Nowadays, you can't get a Scuti. A Scuti's worth nothing. Like a Ducati's worth nothing. I mean, maybe some collector wants a piece of paper, right? So it's a lesson. Like there are value in physical, non-fungible tokens, this original non-fungible token. So, but then a third book is called The Assayer. So what is an assayer? So assayers were kind of like these alchemists, physicists, chemists that would be around a court. And every so often for the treasurer, they would want to accept pieces of gold from the citizens and convert that to script or, paper money. And to do that, they needed someone to verify with a standard of gold that they knew to be gold and do some kind of semi-non-destructive evaluation of the purported object, the metal that was supposed to be gold. So they would take these pieces of gold, theoretically gold, and they would rub it on something called a touchstone. Touchstone was a special piece of rock, granite, whatever. It has no intrinsic value. It's just a piece of rock. But with that rock, you could assay and determine the content of this thing that could be worth, millions of lira or whatever, right? So it's an incredibly important job. And so this person would take this piece of inanimate rock and use it to do something valuable. What I want to do in the Assayer project is take this plethora of physical theories of everything. And I said recently, we should give a Nobel Prize to someone who doesn't come up with a theory of everything, because there's just
that's a good.
There's just like it's just rotten with them, and I think it's great. I often say that theory is kind of like software, and I'm not denigrating software at all, but like you can create a lot of software. You can make a quine, and it'll make its own quine, and like you can make infinite amounts of software.
Look it up, kids.
Yep, that's one of my favorite videos. And you can replicate. You can't make a telescope that makes a telescope that makes a telescope. In other words, hardware is kind of like the non-fungible token that's the ultimate minted, limited edition, the book, the compass book, like I talked. And so it's very expensive. That means you have to be very careful before you invest decades, billions, and humans into pursuing one of these theories of everything. You have to have good intuition for it. And lately, what I've seen is not predictions, but retrodictions. So you see that the Large Hadron Collider will come out with a measurement. And then so-and-so will say, oh, this is compatible with string theory. Or G-2 of the muon. It has these bizarre properties. Fifth force, string theory predicts this. String theory solves this. sterile neutrinos, Large Hadron Collider bottom or B experiment, blah, blah, blah. They'll say that it's compatible after the fact. And it's not so bad, right? Because look, what did Einstein do with GR, general relativity? The first thing he did was not predict something new. He looked at the anomalous behavior of the planet Mercury. And he saw it was behaving strangely. And people had said, oh, that's because there's another planet hiding behind the sun that we can't see that perturbs the orbit of the planet Mercury. And it's called Vulcan. That was one approach. That's kind of like the dark matter approach, where it's like there's a clump of matter that we can't see that's influencing the planet that we can't see, and we use that to divine and intuit the existence of the other planet. That's actually how Neptune was discovered. Neptune was discovered because of the anomalous behavior of the planet Uranus. So Neptune was dark, we couldn't see it. It was tugging on Uranus in a certain way, and that led to Leverrier discovering the planet, predicting where this planet should be found. So it had a good heritage in physics, right? To predict this planet that you couldn't see, that worked. But Einstein said, no, it's caused by the warping and bending of space-time due to the presence of matter, would later become known as the Einstein equations. So he explained why Mercury did that. He didn't, and it was known since the time of Newton that Mercury was behaving in this really freaky way. So he didn't predict it. He retrodicted it. That's fine. But at some point, you should come up with something new that's uniquely predictive of your theory. As I just said, the theory of dark matter in the context of Neptune is actually a valid theory. It just happens not to make sense in the context of Vulcan. And so if he had kept doing that, maybe perhaps he wouldn't have come up with these other predictions that he would later reject. Like, he rejected the existence of gravitational waves. You and Barry talked about that. He didn't actually believe it. It was the one peer-reviewed paper that he had. He used to send, back in those days, he sent a letter to Nature, Physical Review, publish this, I'll let me know how much it costs. And they got it rejected because he said you can't detect gravitational waves. And actually, or they're not real. And the guy showed that they're real because he corrected a math error in Einstein and Rosen's paper. So it's fascinating. What should the assayer do? He or she should look at these theories, look what things they explain that already exist, and look at what new predictions they can claim to explain if we can build experiments to test them.
So you have to kind of challenge yourself to think about what kind of predictions can they make such that we can construct experiments. So that's like ultimately back going to this, to the signal, to the experimenter as theorist, essentially.
That's right.
So like very experiment-centric exploration of the fundamental theory of everything.
That's right. And the best scientists, the best physicists, were both experimentalists and theorists. Or at least that if they were experimentalists, they understood the theory well enough to make predictions or to explore the predictions and the consequences of those predictions. Or if they were theorists, they were like Galileo. Like Einstein has patents for things that he invented. And then, some of his work led to the laser and the maser. So he had it wasn't just pure airy-fairy, quantum reality and expanding universe. So in this case, what I want to do is look at, there's 10 different theories of everything or cosmological models. They make predictions. They have advantages and disadvantages. And I'm just asking the question, why aren't we applying Bayesian reasoning with confidence intervals? Why don't we have updates every time an experiment comes out? We can update our credulity in that experiment, or that theory rather, based on the results of the experiment. And we shouldn't do it after the fact, or as Michio Kaku has said, oh, well, you have to tell me what the initial conditions are. And that's not my job. You're supposed to tell me if string theory is correct. What should it predict if it's true? There's one big problem, which I should say, that to be a good assayer, I think you have to be worldly in the sense of worldly and curious, like we were talking about before with you and Joe. And you can't only talk your own book. You can't only understand your own pet theory of everything. You can't only say, well, I only understand string theory and I don't have time for these other theories, or as if it's beneath me to even go into Garrett Lisi or Eric Weinstein or Stephen Wolfram or aspects of, M theory, et cetera, et cetera. And there are some that say, like, why do we give, string theory so much so much of an advanced past when there are actually predictions it's made that are completely anathema to what we observe in physics. Like the dark energy should be negative, and we see it as positive. Like that's a huge strike. You know, if you told somebody, "Here's my 10-year application," and what do you? Oh, I've made this. If it wasn't done by Maldacena and Witten and folks like that, I don't know if it would have had the traction, the endurance, the resiliency that it's had, and that worries me because all these men and some women are making these fantastic, brilliant, beautiful ideas, and they're not even looking at what their neighbor's doing.
There's a thing that I really enjoyed seeing and I don't see often enough of these theories, which is others who are also experts kind of studying them sufficiently well to steel man the theory,
Exactly.
to show the beautiful aspects of the theory. I see that with Stephen Wolfram. He has a very different sort of formulation of physics with his physics project. Now physics is a foreign land to me, but his formulation, especially in the context of cellular automata or hypergraphs, just as objects, as mathematical objects themselves are familiar. And so I'm able to see the real beauty there, and it saddens me that others in the physics community can't also see the beauty. Like, give it a chance. Give a chance to see the beauty. And that,
give it your respect. So there is one person who does take time and is what I consider to be a great scientist in terms of what he thinks. He obviously has an invested interest in his own theory, and it's Eric. Yeah. Eric's got a truly encyclopedic knowledge of the history of physics. And he has a great warmth and graciousness when it comes to giving others, and I've witnessed this, and look, first of all, I think debate is pointless. Like, I don't know about you, but if you've ever voted like, oh, I saw this debate and, because Trump did so badly, now I'm going to vote for Biden. No, it never happens. You almost never change anybody's mind unless you debate with love, unless you have almost like we're going to win together, like the red team approach in the military. They're trying to win a war. So they may disagree on the tactics day to day, but the strategy, we have to win this war. I love you and I want to protect you. I don't see that in very many of these physicists. From Kaku, I almost see it, it's embarrassing in some ways because they'll almost mock, with the exception of Eric. Garrett's interesting. His theory is, people have a lot of issues, very technical. But Eric has taken the time to try to understand it. Eric has taken the time to understand Peter Voigt's theory. And I don't see the same graciousness extended from them. I'm sorry to say.
Yeah, essentially, you're right. You're right. I mean, with Eric, he hasn't. He wants to, but he hasn't extended the same for Stephen Wolfram because I think.
No, he did. No, actually, no, he did. I had a debate with them live on my show.
No, I did. I listened to it, but like I just think it's outside of the toolkit that Eric is comfortable with. So it's not that he's not. But the main thing that's often absent, and Eric does have, is like the willingness and like not just like dismissing or mocking that he's reaching out. But okay,
I mean, what if it's not? I made a joke when they were on. I was like, how many theories of everything can there be? Highlander, there can be only one. I don't know. Maybe.
But he, of course, also, like the other folks who propose a theory, has an ego.
Yeah.
He rides a dragon, with the dragon representing the ego. Well, let me ask you about your friend Eric Weinstein. So he proposed initial sketches of geometric unity, which is his theory of everything. Maybe you can elucidate some aspect of it that you find interesting. But what do you think about the response he got from the scientific community?
Well, some of the response came from people, academicians, professors. Some came from a lay audience, and some came from trained scientists who are no longer, maybe practicing in universities. I thought there was a lot of vitriol, which surprised me because I look at what he's trying to do, and it was always, the vitriol would always come with some element of ad hominem. And maybe that's his personality, maybe that engenders this or whatever. Maybe there is kind of just a natural tendency. I always get these emails. Professor Keating, I have a new theory. Einstein was wrong. I'm going to prove it. I'm not good at math, but if you help me, I will share my Nobel Prize with you. And I'm like, oh, thanks. Have you read my books? In other words, it's always taking down the dragon. It's always taking down the kung fu master, right? That you get the hit points from D&D. You get their hit points. You take their cards. You get their risk tokens from Kamchatka. And thinking about with Eric, it's like, because what he's doing is so aspirational, it is grandiose in a good sense. What he's trying to do is construct a geometric theory of everything that has aspects of supersymmetry and stuff embedded in it. He's trying to meld that. It has very unusual features, and that it features not only multiple spatial dimensions, multiple time dimensions. It uses new mathematical objects that he's invented. And look, I had had him on my show. I've talked with him. We've had consultations with other physicists, where he'll come down, and I have a visitor's office, and he comes down to San Diego sometimes and spends time there. And we talk with eminent mathematicians and physicists. Eric's been out of the academic world for a long time. And there is, as I said before, an aspect of persuasion that must take place in order to get anything through. And I think there was a slight amount of good nature, not ignorance, naivete, but just the sense that if this is right, everyone will recognize it. If you build a better mousetrap, the world will be a path to your door, as the expression goes. That's completely untrue. That doesn't even happen with mousetraps. I mean, you know how many freaking mousetrap types there are? It's like, no, they don't beat a path to your door. You have to sell that freaking thing. You have to sell it like Steve Jobs or Elon. I've had one paper out of 200 papers I've published in peer-reviewed journals. I've only had one, 0.5% published with no referees' comments. In other words, published like Dream, submitted it, it happened to be in a prestigious journal. So I was pretty psyched about that. But you almost have to crave the response, getting it back from a journal. And I think he doesn't see, first of all, he doesn't subscribe to the peer review process. He thinks that is anathema to the way science is. It vests interest in journals, et cetera, et cetera. I think you can have elements of peer review that are substantive and valuable. I think you have to learn from your critics. One of my conversations with John Mather, he talks about loving your critics in this book, but not being so open to their criticism that their criticism goes to your heart, and not being so open to their compliments that their compliments go to your head. It's a very tough Scylla and Charybdis to walk.
Well, there's something, I want to be careful here because I'd like to talk to Eric about this directly, but I'll just from a perspective of a friend, want to ask about the drug of fame. So there's also the public perception of the battles of physics, and so there's a very narrow community. But then there's the way that's perceived. The exploration of ideas is perceived by the public. And so there is a certain drug to the excitement that the public can show when they sense that you have something big. And that in itself might become the thing that gives you pleasure. And I think that with theories of everything, or with any kind of super, super ambitious projects, and this is taking us back to when you were ambitious about trying to understand the origins of the universe, if you convince yourself that you have an intuition about the origins of the universe, and you have a platform like you do now, where you start to communicate your intuition, it's hazy, like all of science. You're still unsure, but you have a sense. Perhaps you don't have that as much as an experimentalist, because you always kind of start going, okay, how can I build a device that to see through the fog? But if you're more like a theoretician who kind of works in the realm of ideas, in the realm of intuitions, it is also a source of pleasure. You mentioned dopamine. A source of dopamine that you can communicate to others that you're really excited by the possibility of solving the deepest mysteries of the universe. So there's some aspect to which you want to be a Grigori Grisha Perlman and go into the hole and get the work done and shut the hell up about I'm speaking about myself, about, talking planning about the dream and planning and exploring how great it will be if my intuition turns out to be correct.
That's right.
If the sketches I have turn out to actually build the bridge that takes us to a whole new place. As a friend of Eric's, or a friend of or my friend, what kind of advice do you give? What is your role? Is it to be a supporter, given that he has many critics, or is it to be in private a critic? Like a lot of my friends will say, hey, shut the hell up. Just get it done.
Well, first of all, I want to ask you a question I've asked him, and it comes from Animal Farm by
Probably
George.
my favorite book, yeah.
So you remember Benjamin the donkey?
Yes.
And he's talking to the pig. I forget the pig's name. You probably know. Anyway, the pig says to him, you got this long, lustrous, beautiful tail. You're so lucky. I got this short, curly, little squiggly thing that does jack squat. Tell me, how does it feel to have such a lustrous tail? And Benjamin says, well, the good Lord, he gave me a tail to swat away the flies. But you know what? I'd rather not have the tail if I didn't have the flies. So I want to ask you, as I've asked Eric, is it worth it? You know, you've got these beautiful tail, but there are flies. I'm not saying in a negative way. I'm just saying you get unwanted distractions, dopamine, you know, it's kind of the highlight, the spotlight effect. It's obviously allowing you to do things that you could never do alone. And I think, you know, first of all, I'd love to know how you answer that, because that's something I don't feel I can relate to myself.
Well, this has to do with more like
Platform
stuff.
Yeah, scale.
Oh, that has very little effect on me. I enjoy it. I enjoy meeting new people, but that has nothing to do with platform. Yeah, no, that has no effect on me. I'm somebody that enjoys the act itself. So this conversation, the reason I'm doing this podcast with you today is because that allows me to trick you into talking to me for a prolonged period of time. I don't care about platform. No. I assume nobody listens. It really doesn't matter.
Yeah, and if it got it right, my whole test of it was a good podcast. Because how do you know? Like, podcasts have been around, 12 years? How do we know as podcasters we're doing a good job? Like, sometimes someone will say, that was the best interview I ever had, but that doesn't happen that often, at least for me. But if you realize that you forgot to put the SD card in that little guy and the Zoom didn't work, would you do it again? And I think if you say yes to that, that was a good podcast.
Yeah, exactly. That's exactly it. So in that space, yeah, all of it is worth it.
Yeah.
But the dream, I'm more referring to the psychological effects. Forget the platform, forget all of that. You know, I maybe shouldn't even brought up the platform, because it really has to do, even in your own private mind, which is what I'm struggling with. I enjoy the planning, the dreaming, the early stages so much that I often don't take projects to completion. This is a psychological effect that I'm sure basically every engineer, everybody that does anything goes through. I just, in this case particular, I think it also applies. And I wonder, as a friend, what is the role?
Yeah. So, yeah, I mean, that effect has been documented, everything from, planning telescopes to dieting. So there's a tiny bit of dopamine that you get visualizing how you're going to feel. You don't need to know this, but, you don't deal. But losing 5 pounds, I said, I'm going to lose 5 pounds and I'm going to be able to run, a minute faster. So there's a part of me when I'm planning the diet and the meals and the exercise that I get a little bit of that thrill, and that actually saps a little bit of my willpower to actually complete the task that will take me to that goal. Yeah. So that's a documented effect, and that happens in project planning and project management. It's a very, very important thing to guard against as a manager of a big project. With Eric, it's interesting because with him, first of all, we relate extremely well, on a friendship level, and very close. He does remind me a lot of my father. And I've told him that, just as a mathematician, as a big thinker, as, in his case, as a father, the father kind of figure that I didn't have in a sense, but that he is a true lover of life. He knows he's got a huge platform. He knows he gets a lot of attention for what he does. And, I jokingly say, well, it's one thing, like, how do you know, Lex, that someone's an expert? So experts say. There's a good rule Ray Dalio writes about in Principles. He says, an expert is someone who's done something 3 times successfully. Like, you can do something correctly once, you could do something correctly. It's very hard to pull off like 3 projects, 3 telescopes, 3 whatever, right? So look for, it's arbitrary. It could be 4, it could be 2, right? But the point is, look at Eric. So how many things has he contributed to and made, pretty substantive kind of paradigm shifts for different people? I would say he's been right many times. Does that mean he's infallible, that he's ineffable? No, of course not. For me, so what I'm saying is I get a little bit of the joy of kind of learning something purely as a scientist, something completely outside of what I do, mathematics, gauge theory, the kind of very advanced geometry topology that he's interested in. But every now and then, I will sneak in that I want, I've told him, I'm going to turn your son into an experimentalist to spite you. He is not going to be a theorist.
Yeah.
Zev is not going to be a theorist. He is working with me. He is learning from me. We're trying to get him he wants to bypass all of the, kind of nonsense of undergraduate and go straight to graduate school. And I've tried to encourage him that maybe he could do it, maybe he can't, but there's no other way than to try. And so I've prepared a whole curriculum for Zev to basically bypass all of undergraduate. And to his credit, he's done, earns all the credit. He's learned it to a level that matches many of my graduate students.
Okay, hold on a second. I have to push back, and this is me saying it, and I'm sure I'll talk to Eric about this. But to say, you said Eric's was right on multiple things. I think Eric has a great, deep insight about human nature and how societies work. And he says a lot of wise words on that world. But I think if we're talking about experts, you kind of have to prove, it's like Michael Jordan playing baseball. Like he's proved it many times that he can play basketball, but he's also got to prove that he can play baseball. Right. And I would say the whole point of radical ideas is it's very hard to be sitting on a track record of, when you're swinging for the fences always, there's not a track record to sit on. And like Max Tegmark is an example of somebody who has a huge track record of more like acceptable stuff, but he also keeps swinging for the fences in every other world. Right. So he has that track record. Yeah. With Eric, if you look at just the number of publications, all this stuff, he chose not to travel the academic route. So there's no proof of expertise except sort of an obvious linguistic demonstration of brilliance, but that's not how physics works.
So
right?
there's a polite way to damn somebody as a scientist and say he or she they really know the history of physics very well. like physicists always love it. Like Sean Carroll always jokes about it, like physicists should never talk about history of physics. But it's more than that. So Eric has certainly contributed in finance specifically, and gauge theory and economics, and inflation dynamics, and the non-cosmological.
Hold on a second. That's yet to be proven. He has a lot of powerful
gauge theory is calculus. Is calculus proven? I mean, he has a gauge model for currency exchanges between different nations that is explanatory. It's not. Is it something? In other words, it's a model and it's used for pedagogical purposes.
And it might be okay.
It's unique to him. To him and Pia.
Yes. Right. It might be a powerful model. It might be one that's actually deserves huge amount of applause and celebration, but does not yet receive that. And that's one of the things that Eric talks about. It has not received the attention it deserves. Yeah. But it has not yet received the attention it deserves. And so like the proven expertise thing, there's a lot of people that go to their grave without the recognition they deserve. And it's a tragedy.
Sure.
But the fact is, like, you have to fight for that recognition. The tragedy happens for a reason. You can't just say this person is obviously brilliant and therefore they deserve the credit in every single domain. It doesn't like transfer immediately. There's nobody that's, well, at least I wouldn't argue Eric is one of the special minds in our generation. But you still have to fight the fight of physics and prove it within the community. And I think the same applies in economics. You can't, as somebody that, I've gone through the academic journey, just like you said, the peer review, all of those things, flawed as they are, that's the part of the process. You have to convince your peers, the people that are as obsessed for whatever the hell reason about that particular thing that you're working on. Yes, there's egos. Yes, there's politics. It's a giant mess, but I think it's a beautiful mess through which you have to go through in order to reveal the power of your idea to yourself and to the world.
Well, let me use an example. So, you know of James Clerk Maxwell, and he invented the laws of electromagnetism, which is the first example of a unification principle ever displayed by the human mind in history. Purely mathematics, unifying completely disparate phenomena. In one case, electricity, charges, static electricity, lightning, and the other magnets, bar magnets, currents, etc. Unified them. You know what he did? I like to do a thought experiment. So imagine Twitter exists 1864. Maxwell's working away, and he goes, I have this wonderful idea with fluxions and inductive virtue and blah, blah, blah. And it revolves on this thing called an ether. And by the way, there are these little vortices and gears, and the gears have these planetary things, and they suck up vortices, and the vortices determine the density of the electromagnetic potential. You'd be like, this guy's a freaking moron. And what would you do? Come on, honestly, you would say that everything this guy does is wrong. I mean, he's got this idiotic idea, and it would be falsified a couple of decades later by Michelson and Morley. And in so doing, you would have thrown out a very beautiful baby with bathwater. Imagine Twitter. Imagine the twit storm. Clerk Maxwell at Clerk Maxwell 1 would get. It would be brutal, right? And to the detriment, and that might even set back history. Imagine Yang Mills doing the same thing. Chern Simons. A lot of these things are very fantastic. But why, Lex? Why does Ed Witten? Why does Juan Maldacena? Let me give a good example. Juan Guest, brilliant guy, I love him. He is the reason that Stephen Hawking conceded his black hole information paradox loss issue. What did he concede? Conceded based upon Maldacena's calculation in ADS CFT and 5-dimensional wormholes. Is any of that? First of all, we don't live in an ADS universe. Second of all, we don't know if wormholes are traversable, if they exist even. These are devices. Kip Thorne is popularized for movies. Is like to say that this is something on which I will concede a bet. Now, obviously, Hawking was doing that for publicity. Why does Maldacena? And he's got a pretty high H index, pretty well-respected guy at IAS. Love talking to him. Brilliant guy. By the way, also had made use of Eric and Pia's work on gauge theory and economics originally, and won, I believe, the breakthrough prize. I can't remember exactly what, but partially, credit some of the work that he did, which appears there's a footnote to Pia Milani's thesis and some conversations with Eric, I think, in it. Anyway, getting back to that, why is there not the same skepticism? Is it because Maldacena, who's an eminent physicist, obviously, has published, realistic work and done. What about Witten? Witten gets a pass. I mean, if you
Witten gets a pass on which aspect? The string theory?
Well, yeah, that M theory is correct. I mean, let me just say Hawking. Hawking gets the ultimate pass. Hawking would say things like M theory. There's zero evidence for it. I mean, there's the famous meme that went around this weekend, like, what has string theory predicted? And it's nothing. And by the way, that's actually wrong. I talked to Kamran. I know you talked to Kamran. Kamran says that string theory does make predictions. It predicts the mass of the electron lies between 10 to the minus 1 Planck mass and 10 to the minus 30 Planck mass. Okay, whatever, our electron mass.
It's a big range.
It's a huge range. Imagine Kamran comes up, and again, he's just some nobody, but he actually, he doesn't have a profile. He's not at Harvard. Has 0 H index or whatever Eric's is. Why do we not in other words, why are we more harsh on people that are trying?
The answer to that. So I get a million emails, just like you said, you yourself, where they prove in my world, it's artificial intelligence. The equivalence of that is I figured out how to build consciousness, how to engineer intelligence, how to sometimes
you should send your emails to me, and I'll send my emails
and
to
we'll reply to it. I mean, I don't want to sort of mock this because I think it's very possible that there is either kernels of interesting ideas or in whole, like there is geniuses out there that are unheard, but because there's so much noise, you do have to weigh higher the Ed Wittens of the world when they make statements. And that's why you build up a track record. As you said with Ray Dalio, you have to show that you can, if you're Pollock and you show us a painting of a bunch of chaos, you have to, and this is a bad example probably because he probably never showed this proof.
He could do it, right?
Yeah. It's much more comforting to see that they can paint a good accurate picture of still life of an apple on the table. So there's
meteorite at a time.
Because then because then there's something about the scientific community that they have perhaps an oversensitive bullshit sensor to where they're not going to give the full effort of their attention if you don't have the track record. Now, you could say that's a kind of club that only you have to have 10, you have to have this. Yes, that exists, but there's some aspect in which you have to play the game a little bit to get the machine of science going. Otherwise, if you're always saying, well, I have my ball and I don't want to play your game sucks, right, then nobody's going to want to play with you.
That's true. And there, look, inherent in all of this is an underlying grandiosity. Look, how could you talk about doing what Kaku said on here and elsewhere? You know, we're looking for the umbilical cord that connects our universe to another universe that will then reveal in a 1-inch equation that will surely win a Nobel Prize, the mind of God.
That's like a prerequisite, I guess, to tackle these questions.
I think it's detrimental. I think doing that, first of all, I think there's an element of almost snarkiness because none of these scientists are believing, Gnostics. They're not theists, right? So they're using it as kind of a stand-in, and they always talk about Einstein. And he was like a Spinozan, and he wasn't a theist.
God doesn't play dice.
God doesn't play dice.
Einstein's mentions of God. Yeah.
Yeah, and then Stephen Hawking says when we get M theory understood, we'll know the mind of God. That's the title of Kaku's book, The God Particle, The God Equation. Do any of them really believe in God? No, is that a prerequisite? No, I'm not saying that. But the point being, you're talking about something that has to do with God, right? I mean, where else do you go from there? I mean, I think God for now enjoys a little bit more, kind of PR than Elon or Joe or whatever, right? So like it's, God's got a pretty good, H index himself.
He has by the way, a Twitter account, just so you know, it's pretty good.
The tweets of God.
Yeah.
That's right.
Tweet of God.
So if you look at that, you have to go in there. Again, you have to go in with some swagger. You have to have a little bit of arrogance, but you should, I agree, mix with a little bit of humility. So he's doing something. He comes from outside of academia. Now, if he rails against, I'm talking about Eric now. If he's just railing, the system, and I'm not going to publish because F that, and that's only created by greedy journals, I don't think he's doing himself any favors. On the other hand, if he's shopping it, if he's talking it, if he's willing to expose it to criticism and to even embrace people who may not have the purest intentions, perhaps, but in the sense of like they're not arguing solely to get to the truth with a capital T. What they're trying to do is take down Eric. Hopefully those people aren't out there. But on the other hand, looking at what Eric does for other people, looking at the fact that he has courtesy. He will look at Wolfram. He will look at Lisi, who's one of his closest friends. I mean, he calls him not his
nemesis.
Nemesis, right.
Yeah.
And I think that's interesting that they're loving friends.
I really enjoyed that portal conversation between Gary Lisi. Eric is torn about that conversation because, I guess, because of the nemesis of the beautiful dance of minds playing with these ideas of theories of everything.
And some of these things, look, so fundamentally, now I may disagree with him, Eric, on a different aspect, which is the only one I'm capable of. But let me say one thing, which is experimental. But let me say one thing. I understand probably a third of what Eric's talking about with GU. I understand, GR. I understand mathematics. I understand some group theory, fiber bond. I can get a little of it, the age theory. But I also understand what I don't understand. And I understand that there are people like Witten, Maldacena, Nima, other people that can understand it. And they're not trying to understand it. Sabina, she can understand it. She makes all these, I don't understand it. I don't want to understand it. I don't have time. And then she makes a music video, kind of mocking Eric and Steven and Garrett.
Yeah.
I'm like, you have a time to do. And I love Sabina, and I've actually promoted my show on her, and I love her, and she's doing a wonderful job. But you have a video that you said yourself takes 8 weeks to produce from start to finish, and you couldn't have spent 30 minutes, 2 hours. Brian Keating, have done it as an experimental cosmologist, and I have enough to say, like, this is interesting. It's part of the Assayer project, and it actually, I shouldn't say that there are no people. They're very serious. Louis Alvarez Gomez at SUNY Stony Brook, Simon Center for Geometrical Physics. So he and I are running this seminar. Hopefully this summer, we're going to reenact the famous Shelter Island conferences in the 1900s, where Feynman got together and they calculated the Lamb shift and all. But what did that feature? The harmony, the resonant minds behind the best experimentalists in cosmology, particle physics, condensed matter physics is now teaching us tremendous things about lower dimensional systems that can be applied. Theorists and experimentalists, observers, cosmologists, astronomers, we all will get together, and we're just going to do it out of a spirit of love. But if it's just like, this guy's like a loudmouth, I don't have time for that. I really don't. I don't think it's interesting way to spend my time.
There's a aspect that I hope to see, and it goes back to our sort of discussion about Joe Rogan. I do hope to see sort of love and humility in the presentation. Like, let go of this kind of fear of your ideas being stolen and the ego that's inherent to the scientific pursuit. And
Right.
now that everybody is established and known entities, let go of that a little bit so we can explore and celebrate ideas. I would love to see more of that, just like as you're saying, especially with these big ideas of theories of everything.
And I've talked, I mean, this isn't talking tales out of school, but I mean, he has made claims that I fundamentally disagree with, in terms of like, he's had this Twitter baiting, loving trolling of Elon. Why are you spending all this money to get to Mars? We should be spending money on interdimensional travel and we can unlock it if we. And I said to him, like, and he makes the point, that, the atomic theory, that unleashed the nuclear age and that, could lead to planetary destruction. But I make the point pushing back with love on him. And I say, look, nobody looked into the equations, like Fermi didn't look into all these equations of the unification, which still doesn't exist, by the way. We spend all this time, Lex, and I don't know why it is. It's a phenomenon purely in theoretical physics. People are looking for the toe and they're overlooking the gut. In other words, they're spending all this time on the theory of everything, the God equation. And there's this gut that unifies the three stronger forces. We don't have a single theory for that. And people like Glashow, they've tried and failed at it.
Yeah, for people who don't know, there's 4 forces, gut, grant, unification theories that unifies the 3 forces stuff, and done trying to get a shortcut to the theory of everything, which unifies the 4. And then there's this whole thing that maybe quantum gravity is not even a thing.
Right.
So, so we're trying to solve. We're trying to solve the puzzle of everything at the physics level. And then already before solving it, already saying, once we solve it, here's going to be all the beautiful.
Or just like level jumping it. Yeah. Going to level 256.
10xing thing. Yeah. I mean, I suppose you need that kind of ego, that confidence, that ambition in order to even have a chance at some of these.
The only 2 people in this book of 9 Nobel laureates who told me they don't have the imposter syndrome were 2 theorists, Frank Wilczek and Sheldon Glashow. And, Frank is pretty interesting. I know eventually we're going to talk about the meaning of life, but you talk about Frank. Frank invented this theory along with his advisor and a third person in the early 1970s, which from 1974-3 when he was at Princeton, all the way up until 2004 when he won the Nobel Prize, every day of his life. Imagine this, Lex. You're going to have this startup. Someone tells you you're going to win the lottery. You're going to win the lottery in 40 years. What becomes your singular focus in your life from now until the next 40 years?
Well, I'm not sure. I mean, would it be winning the lottery, or if I'm so confident?
You're guaranteed to win a lottery.
Yeah.
Here's this wallet, Bitcoin wallet. It's going to guarantee to have this much money. It's stable coin, whatever. You're going to win it 40, but you have to wait 40 years. To me, it would be surviving for the next 40 years. You wouldn't leave your house. You would go out in a bubble wrap hat. You wouldn't go out with that 20 masks on, right? Your whole life would be consumed with. Now imagine everyone's telling you you're going to win the Nobel Prize, which is bigger than the lottery. I mean, many prizes are worth more than the Nobel Prize. And every person who wins a prize that's worth 3 times the money, like Maldacena, he would trade the breakthrough prize for a Nobel Prize in a heartbeat. So these guys had to wait 40 years. Imagine the excruciating pain. What got him through it? He didn't feel like he didn't deserve it. He felt like, hell yeah, I earned it. He has that swagger. And what I'm looking for in this assay is to try to find ways that we can test stuff now, because I don't know if I'm going to be here in 40 years. I hope I am. But can we bypass? Can we get shortcuts? What's called the low energy regime? And to me, that's what's interesting. Like, what can we do now? I don't care. Like Isaac Newton came up with color theory, and he did something really interesting. Next time I come, I'll bring you some prisms. So what did he do? He took a white light, he took a prism from the sun, actually. He put it through a slit, put it through a prism, and it made a beautiful rainbow, like you've seen. And then he took another prism, and he put it upside down, like, dark side of the moon or whatever. And the light went through the first prism, turned into a rainbow, and then the rainbow went into a prism and came out a white light. Mm-hmm. That's pretty cool. Then he took a popsicle stick or whatever, it's probably pipe tobacco, and he put it in the beam, like blocked out the orange, and it didn't make white light come out. He showed like colors of synthesis. It's a combination. He didn't use like the Large Hadron Collider to do that. He used a very low energy experiment to prove a unification in this color physics and a different kind of color physics than in quantum chromodynamics. But nevertheless, can we find things like that? Are we spending way too much time and energy thinking about the future circular collider, which even if it gets built will cost $30 billion just to build? By the way, anytime from now on, if I leave you with anything, anytime an experimental physicist tells you a number, always double it, maybe triple it.
How much is it going to cost?
To operate it. So like, do we build an aircraft carrier to build an aircraft carrier? Do we build a nuclear reactor, a semiconductor facility? And the rule of thumb that works pretty well in project management is it costs about 10% per year to operate a given object of sufficient complexity. And in this case, so in 10 years, it'll cost double the cost. So never believe a number, whether it's from our mutual friend Harry or whoever. Don't believe the number, double it, and then say, is it worth it? And so building a solar system size accelerator, even if it were possible, do we have to do that? Or can we use these two 30 solar mass objects colliding together to test the number of large extra spatial dimensions? Can we do that? People are working on it. I think it's fascinating.
So focus on building detectors.
Experiments.
That, like, where the cosmos is part of the experiment, I suppose. That's doing the hard work. Because when you're saying low energy regime, because for some of these, especially big questions like theories of everything, you need some high energy events. And so somehow figure out how the high energy events that are already happening out there, how to leverage them to understand here on Earth.
So one of the alternative theories of cosmology that is not singular, quantum gravitational requiring, as the Big Bang and inflation are these bouncing models. Some of them feature a similar kind of entity called a quantum field. And that quantum field in the initial stages of the universe of our current, after the bounce, which is not a singularity, it compresses to a classical kind of rebound, and the universe starts expanding. During that process, the expansion is governed by what's called a scalar field, of which we only know one that exists. That's called the Higgs boson. Higgs is a scalar fundamental particle, fundamental field. That field then later does double duty, and it becomes dark energy. So it solves two problems. And I'm not saying it's correct. We don't know yet. But are there observations of, and so dark energy is manifest today. It's manifest in properties we see in supernova explosions, et cetera, et cetera. We see the effects of accelerating universe caused by presumably dark energy. Is dark energy a constant, or does it vary? That has to vary in order for this theory to be true, because that eventually has to decay so that the universe can not support itself and collapse again classically. So we could use low energy phenomena. It's hard to think of supernova as being a low energy phenomenon, but we use that as a tracer of the cosmic expansion field and see, does it change or is it a constant? That's an example of a low energy limit to prove a high energy phenomenon like this collapsing universe in the cyclic model.
Speaking of things that cost a lot but are super exciting.
Yeah. Page 2. Oh, crap.
No, we'll wrap it up.
No.
Calm down. There's more than page 2. What do you think this is? This is
thesis. Actually, well, Louis de Broglie's thesis was 3 pages long, and he won the Nobel Prize for the wave-particle duality.
So, size matters in different dimensions in life. I think the lessons I've learned about life is the shorter the paper or the shorter the thesis. Actually, the shorter the paper, some of the greatest papers ever written are short. Like I feel like some of the best ideas in this world, now not to sound like a contradiction of Feynman, a contradiction on top of a contradiction, but it could be written on a napkin, honestly. It's just kind of what tells you something about ideas. What are your thoughts about the James Webb Space Telescope? Is this, as somebody who likes telescopes, and this is one of the, I think it says, it took 20 years to build, $9.7 billion. Is that way too much, too little? Are you excited about this thing?
It's sufficiently different from what I do in my field that it's incredibly interesting to me, because it's I have no horse in that race. And so I'm not competing with them for time or money or resources or people or whatever. So I can purely be an advocate and an aficionado of science. It is, in some sense, the successor to Hubble. It will do things that Hubble can't do. It will also may or may not have the impact on a visceral kind of artistic level that Hubble had. What are some of the most iconic things that Hubble did? The Hubble Ultra Deep Field, the pillars of creation, storms and imaging of these twisted deep sky galaxies. Those resonated with the public.
Just visually, they were beautiful.
Visually, yeah. When you look at these images, the Hubble Ultra Deep Field, you'll maybe put that in. You'll show every speck of light except for 4,000 blobs of light. There's one star in our galaxy. The rest are galaxies. Now, that image is less than 1/10 of your fingernail held out at arm's length. It contains 4,000 galaxies. So now you can figure out how many galaxies there are in the whole sky just by seeing how long does it take you to move your fingernail over the whole sky. So we have another couple of hours. No, so it comes out to be, that's how we get 500 billion or more galaxies. Now, it's not exact to the galaxy, but it's a good order of magnitude estimate, maybe even better. Hubble produced that, and it was basically serendipitous. They pointed to some dark blank piece of sky, what they thought was blank, and they saw it. Same thing that happened with the CMB. They were looking for something they didn't find. Same thing they found when they were looking for the deceleration of the universe and found it was accelerating. So what I sometimes hear is that we don't know what we're going to discover. I never think that's a good idea to spend billions of dollars on something. Like, you should have some guaranteed low-hanging fruit, and then there should be swinging for the fences. And I think in this case, it was really everything is swinging for the fences, because it's kind of a single point failure. If that telescope, which is this origami construction of 22 hexagonal panels that have to unfold properly and then orient themselves 1,000,000 miles from Earth, beyond the Earth-Moon distance by a factor of 4, and still transmit telecommunication back to the Earth, get solar energy, keep it away from the sun. You don't want to look through the telescope of the sun with your remaining good eye. And you do that, and you cover. It's going to be phenomenal. For science, for sure, if it works. There are a lot of people think, it's so risky. NASA sunk so much of their budget. It ate up, and what if it does fail? I mean, there's no guarantee. Yes, it's insured, but so what? You're not going to get back those 20 years of people. Well, let's start building it again. Like, they didn't build 2 copies of it.
Then if it fails, it kind of has a dampening effect on the prospects and the inspiration of the public for what science can do, what science engineering can do is out in space.
It will make a huge impact scientifically. Let's hope for the best. Let's assume it does succeed. It's launched in a couple of weeks. And when it does, it will transform our understanding of, we just discovered not only like extrasolar planets that have moons on them and asteroid belt. We discovered an extrasolar planet in another galaxy. This will be able to see crazy stuff like that, spectroscopy, imaging. But it'll be able to go back farther in time, such that we will be doing cosmology. Like, Hubble did some cosmology. It measured the Hubble constant. That was its key project when it was designed and launched. But because it is an optical telescope, it's sensitive to more, close-in redshift, so shorter distances. Now, James Webb is much, much higher redshift. It can probe the darker, deeper, distant universe.
Okay, let's talk about not the distant universe, but our neighboring planets. First, I got to ask you about the moon. So there's a piece of the moon on this table that you've given me.
Yes.
That we didn't have to pick up, that arrived here.
That's right.
So how did a piece of the moon arrive here on Earth?
So this chunk of the moon, if it were delivered by the Apollo and NASA missions, you and I would be guilty of a felony right now, because it's illegal to own pieces of the moon collected by the Apollo astronauts. So don't even joke about that when you go over to Houston. This piece of moon rock was delivered via the old-fashioned way, by gravity. So this was a chunk of the moon, which is blasted off because the moon gets bombarded by asteroids and meteoroids. Some of them eject material from the surface of the moon into space. And it will then orbit the common moon-Earth system, and it will then eventually enter our atmosphere. And if the piece is large enough and the trajectory is proper, it can land intact. And this one landed with a few 100 grams worth, and they sliced it up. And then it was delivered via U.S. Postal Service to my house. So you can buy these pieces. And actually, you can buy a piece of Mars. You can buy a piece of Mars delivered by the same route. Now, what's so interesting about that? Well, if a piece of Mars can get here, a piece of Earth can get there. If some piece of Earth has some life forms on it, it could get there. And if that can happen in our solar system, it could happen throughout the galaxy. So I'm actually not of the opinion that there is life elsewhere in the universe, at least technological life that we can see. I see this look of horror on your face. I view it, I am personally extremely pessimistic, would be extremely surprised.
I'm curious by the transition, because you just said that life could have arrived from Mars or like from planet to planet, but because of the meteorite striking it and so on.
Yeah.
And then you went to, you don't think there might be life out there in the universe?
Technological life.
Yeah. Advanced intelligent civilizations. Okay. Okay. So go on.
Yeah. So that's the generalization of what the famous astronomer Fred Hoyle called, I know this is a PG-13 podcast, it's called panspermia. Panspermia. And
beep that out, please.
Yeah, please. And that's the exchange of genetic life form material from other reaches on Earth, which explains the origin of life on Earth, but not the origin of life itself, which I think is a much grander mystery and much more interesting. How did life get here? And you've talked with many eminent people about that. I'm not going to add that much, but just thinking about the reverse process. Let's say life started on the Earth somehow, and then made its way out into the universe. Is there enough time for the whatever material went from Earth via panspermic direction, spraying the love gun out into the universe? Did that then have enough time to incubate and go onto a planet that could support it? Certainly not within our solar system, which traveling at the meteorite speeds would require, hundreds of millions of years. Then looking at the evolutionary history from bacteria to Bach, from, rocks to Rachmaninoff. I don't know. I can do this all day.
Oh, wow. That's pretty good.
How do you get from those very simple inanimate objects to life? I just simply think there's not enough time for Earth to seed life, technological life throughout the galaxy. I don't think there's any evidence for that.
But so you really think that the origin of life on Earth is a really special event?
Yeah. If it did originate on Earth, my question for those that search for life outside the Earth is, what if you had a letter from God and the letter said, life didn't originate on Earth? Like, would you choose a different profession? Like, it would seem hopeless. Like, in other words, we only have a sample of one. In fact, we only know of one conscious life form, let alone one planet that has life on it, right? What if you knew for sure it didn't start here? That means that, like, there's almost nothing about Earth that is originated. It didn't originate the life process. So to study purely the origin of life, not life itself, I think that's still fascinating. But how could we learn about, the origin of remember, you have to go from inanimate object to a living object, whatever that definition of life is. And I'm not an expert in many definitions, Max, Sarah, many different definitions. But how do you actually go from inanimate to animate? It's a huge question.
Yeah, but then you don't have to be the place where life originated to replicate the origin or to that's one way to understand something is to build it.
Yeah.
But another way is to just observe it. You don't have to truly re-engineer from scratch.
Yeah.
So but then yes, if it didn't originate on Earth, then your intuitions about the basic prerequisites of life are off.
What's the governing principle, right?
Like, what is and then you can have just almost an arbitrary number of possible, like, if life didn't start on Earth, to me that's exciting, because it's like we know even less than we thought. The thing is, it can prosper on Earth though.
Yeah.
So maybe the origin of life is fundamentally different from the maintenance of life.
Right. And maybe the existence of the Earth life symbiosis is critical. I think Sarah, you talked about Sarah Walker, that it's a planetary phenomenon, et cetera, et cetera. So doesn't that make it less like, in other words, like, not only do you need special life conditions to create life, but then sustenance of life, as you say, that also has to be maintained under very specific circumstances by very specific planets and with very specific tectonic activity and moon. And by the way, you need a Jupiter nearby. You need an Earth and a moon system so that you don't get bombarded too early. And I always think like this, like technological life. I haven't said this before, really, so I'm just speaking. I usually like to write down before I say this different thing. But one of the things I thought about
somebody hosts a podcast. You should probably accept the fact that you're going to say stupid things every once in a while.
Not every once in a while, every while. I claim that, to get to sending, people to the moon, our planet needed whales and dinosaurs, right? Like, you don't make a solar panel from another solar panel. Like you made a solar panel from a factory that melted down glass, silica, aluminum, extruded that using fossil fuels. Where do those fossil fuels come from? Like, so any civilization that's going to be a Dyson, Kardashev, did they have dinosaurs? Like, did they have like prebiotic life? Did they have a great oxygenation event? Did they have a dimorphism between prokaryotic, eukaryotic? All those hurdles, let's say you give each one, let's say there's 8 hurdles. And each one of those has a probability of 1 in 1,000 to go from, eukaryotic, prokaryotic, whatever. Let's say that's a 1 in 1,000 chance. I think it's like 1 in 10 to the 40th or whatever, if you really do it. But let's say it's for generous nature, 1 in 10 to the 3. Let's say there's 8 of those hurdles. That means you have 10 to the 24th power, different possibility, and that's just with 8. Like the moon has to be there, Jupiter has to be there, dinosaurs had to be there, all the different things that we have to get to technological life. There's only 10 to the there's 10 to the 22nd, we think, planets in the observable universe, not the galaxy. So that's 100 times fewer than the probability to get 100% clearing these 8 very low hurdles of 1 in 1,000.
That's fascinating, because now I really need to listen to your conversation with Lee Cronin, who I believe you had, because he believes the opposite.
Yes, I know. Yeah, I want to have a debate with him.
He believes that the way biology evolved on Earth could have evolved almost an infinite number of other ways. So, like, if you ran Earth over and over and over, you would keep getting life, and it would be very different. So, it's the fact that our particular life seems unique is just like, well, because every freaking life is going to seem unique, but it'll be very different. It's not like we shouldn't be asking the question of what's the likelihood of getting a human-like thing, because that seems to be super special. It's more like, how easy is it to make
slime mold
anything that has the skills of a human? And I don't mean like something with thumbs, but achieving basically a technological civilization. And according to Lee, at least, it's like it's trivial.
I know I fought a little bit. I'd love to debate him. I think it'd be a lot of fun because we debate with love. When I talk with Lee, I love him and he loves me, I hope. But let me ask you a question. I asked this of him and Sarah on a Clubhouse once. So what do you think would happen the next day? Let's say we discovered life. It's Proxima Centauri B. It's it looks just like slime mold, like you got on your brie cheese or whatever. We discover it. What would happen the next day? And they were like, "Oh, this would be transformative." And I'm not trying to be like total Cassandra about this, but I said I don't think anything would happen. And they're like, "What are you talking about? It would be transformational." I'm like, I stipulate that life exists. Go down to like the river. I'm in San Diego. Go down to the Pacific Ocean. Scoop up a glass.
Mm-hmm.
You're gonna find life in there. And what are we doing? What are we doing to our Earth? We're destroying it callously. We're like pumping crap into there. Like we have this toxic waste spill a couple of months ago in San Diego. I couldn't go to the beach. Let me take it a step further. Do you know how many people, I'm sorry, that you do know, but how many people died in the 20th century? Killed. These are advanced civilizations. This isn't slime mold. We kill, we maim, we harm, we hurt, we hate. I don't think anything would happen the next day. We go back to what we had. And I said, if that weren't proof enough, life has been discovered at least 2 or 3 times just in my professional career. Once in 1996, these Allen Land Hills meteorites in Antarctica, so like microbial respiration processes. Still, we don't know. It was a press conference held by Bill Clinton on the White House lawn that's featured in the movie Contact, repurposed for that movie. And then there's this phosphorus life, this toxic life in the pools of Mono Lake. Many extremophile. We don't give a crap. We continue to so why are we thinking that like our from whence will our salvation come, as the Bible says? Like it's not going to change how we are. It's not going to magnify how I treat you or you treat me. And we're pretty knowledgeable people, you and I, compared to, lay people.
Okay, that's interesting. That's a really interesting argument. I wonder if you're right, but my intuition is I can maybe present a different argument that you can think about in the realm of things you care about even deeper, which is like what happens once we figure out the origins of the universe. Like, how would that change your life? I would say there are certain discoveries that even in their very idea will change the fabric of society. I tend to see if there's definitive proof that there's life, and the more complex, the more powerful that idea
No, I
is
agree.
elsewhere, that I'm not exactly sure how it will change society, because it's such a slap in the face. It's like such a humbling force, or maybe not, or maybe it's a motivator to say, yeah, I don't know which force would take over. Maybe it would be governments with military start to think like, well, how do we kill it? If there's a lot of life out there, how do we create the defense
How do we
systems?
extract it, or
Or mine it
Mhm.
for benefits? All those.
I mean, I just see like there's 100 million literal counterexamples of that. I mean, right now there's like 700 million kids in poverty, and like we just how do we go about our life and just not deal with that? I mean, I put it aside. I eat hamburgers, and I, in 100 years I'll be canceled for being a carnivore or whatever. But so obviously to get through life, you have to make certain compromise. You're not going to think about certain things. But I just think there is a sort of wish fulfillment. Like every time there's water, why are we going to Mars and digging and flying this cool ass helicopter? We're looking for water. Like stipulate that water was there. Like I believe there was water. I think we should investigate and see what the geology was like.
But don't you think? So you're saying,
Don't think you're going to get meaning from it. That's all I'm saying. I'm not saying it's not worth doing. I'm just saying there's a wish fulfillment aspect that people will find meaning for life from science.
okay, but there's a complicated line here. What if it's this intelligent civilization living, obviously probably not on Mars, but somewhere like in a neighboring galaxy that we in a neighboring
Star
system that we discover? Don't you think that had a profound change in meaning?
I mean, I guess again, I assume that because of this panspermic process or whatever, that the probability is much, much greater than zero. I mean, it's not 100%, but it's much likelier than not that at least some living material from Earth has ejaculated itself into the solar system, into the universe, right? Into our galaxy.
Beep that, please. As well.
That's right. So I like the fact that that could happen, and that you're holding a piece, from a planetary body, one that couldn't support life, as far as we know. But I could give next time if you play nice and you come on my podcast someday, I will give you a tiny chunk of Mars. So Mars theoretically could support stuff, right?
Moving on up.
So yeah, so I believe that there could be remnants of Earth in this. So that means there could be evolution. I don't think there's any chance that there's people using iPhones and having podcasts and stuff in Proxima Centauri.
There's some chance though, right? So
Again, I think obviously the simple statement to say it's much, much, much higher probability that life exists than technological life exists, right? I don't think we can argue that. It doesn't mean it's forbidden. Again, I'm not saying any of this is forbidden, not worth studying, not interesting.
It's a likelihood thing.
Yeah, and to answer I think you're wise to push back and like, what does it matter what I'm doing? And I like to think about that. Because it's like, what is the value of what you're doing? Like, you have to answer that question, or else at the end of your life, you'll have these existential, kind of crises, right? So when I think about like who I am, part of my identity is answering and asking scientific questions. For me, though, there is a religious kind of undercurrent that does undergird, in some sense, this quest. Again, I'm not like I'm not like wearing a yarmulke, like I'm not like full on into my birth religion, Judaism. But at the same token, I think one of the things Einstein did say is that, religion without science is blind or is lame, and science without religion is lame, is blind and lame. Anyway, the point is that like you can't get meaning, from just knowing facts. Like Wikipedia knows more than all of us will ever know, right? It has no wisdom. Wisdom, it means, sapient. The word wisdom in Latin is sapient. We are wise. And by the way, do you know our real name is Homo sapiens sapien. So it's man who knows that he knows. Do you know what he knows? Do you know what the knowing is? It's that he's going to die. We're the only creatures that know that we are going to die. We don't know when we're going to die. But like, I have a cat, a fierce attack cat. It's beautiful. She doesn't know when she's going to die. It doesn't mean I'm more valuable.
So the survival instinct it's fundamentally different from like the knowledge of death. And that's where the Ernest Becker comes in with the terror of death. Correct. And that's a creative force that seems to be more feature than bug about the human condition, is that, it's a gift of knowing our own mortality. To me, that's why, I agree with you in some sense in terms of the aliens not being a thing that solves all mysteries. That's why, my love has always been the human mind. So understanding who we are, what the hell are we? And I think your love has been an echo of that, which is, where did we come from?
Yeah.
Or basically, as cheesy as it sounds, Michio Kaku has a way with words. If you can just like enjoy the,
he speaks in complete. He's like Sam Harris of Cosmology. I mean, he speaks in complete paragraphs.
But like also unapologetically, he says, we will know God, or we will know the mind of God, or whatever the quotes, those kinds of things. That's exciting. That physics might be able to find equations that unlock our origins at the very core, and like the fabric of it all too, not just our origins. What's up? What's at the beginning. Something tells me we're too dumb to truly understand what's at the beginning. But
I think we should be humble in that way. I mean, again, another thing is, you ever hear the saying like we share 99% of our DNA with chimps or bonobos or whatever? I share like probably more than that. Sometimes I wish we shared like 100%. Like that would be so much more interesting. Like, there's 50% of a fruit fly or banana. Like no. There's something, but that should make us feel more precious. And I almost feel like discovering life on another planet, whatever solar system, would cause a diminution of humanity. Like the one thing I do hold fast to from religion, I don't know where I am with God. Like, do I believe in God? I think that's an unanswerable question. But I have some thoughts about it. But by the same token, I think the one thing I do get from religion is that every human has infinite worth, because we are, in a religious capacity, considered to be equal to God. In other words, we are gods, not to be like, but we can contemplate what God did. We have aspects of God. We have free will. God had free will, if he exists. Again, I can't prove that God exists. Otherwise, you wouldn't have any credit for believing in God.
This is interesting. I mean, it's like I'm talking to Einstein here, but let me ask anyway.
Can you clip that for my clips chart?
For somebody who's looking at the young universe, at the early universe, and are talking about God and are agnostic, who do you think is God?
So I thought you had just like one of the best podcasts with Sam Harris this past summer. And one of the things I liked about that conversation is he talked a lot about happiness and meditation. And he said something that's really resonated with me, and I've been working it around and trying to work on it my own way. But he said, like, you can never be happy. You can only become happy. And I've tried to take it a little bit further than that, because I think it's interesting. Like meditation is like, you're not like, oh, I'm happy, and now like, oh, my kid came in and now I'm not happy. Like, no, like you can be satisfied. Kurt Vonnegut said, like, you ever catch this sometimes, Lex? You're like walking around, you're like, life is freaking amazing. Like, I'm happy. And Kurt Vonnegut said, you should say to yourself every time that happens, like a little mantra, like, if this isn't goodness, if this isn't happiness, nothing is. Just remind yourself how awesome it is every breath, everything that you do when you make an impact, even some of the bad stuff that happens. Good. It's good. So Sam said that, and it made me think, because I was like, well, what does it really mean to be happy? Because like I can think of about 2 or 3 ways that right now I could double my happiness. Like win the lottery or whatever. Like I could double my happiness. There's only a few ways though, right? Like, I had this kind of thought, like, how many boats can you water ski behind? Like you had twice as many followers. Now you got 2 million followers, 5 million, whatever. It doesn't do anything. It's called the hedonic treadmill. Like once you get to a certain level, it takes a lot more, change in followers, money, impact, women, whatever you want to make you have one more quanta of happiness, right? On the other hand, this is a concept from entropy. I could make your life miserable in an infinite number of ways. In other words, there's more space to make your life unhappy than happy. And so I thought about that in the context of what Sam said about happiness. So it's sort of like, it's an expression of entropy. And that what you should be doing in life is doing that which will cause you devastation if it goes away. Because those are the things that like are where you're reducing entropy, like a kid, like anyone who's a parent knows instantly what I'm talking about, like how to make your life a billion times worse. But there's no way to make your life a billion times better. And so thinking about that, now turning into the question of God's existence, I feel like there's no way that you can believe in God, to misquote Sam, but there's ways that you can become a believer in God. In other words, you could increase the Bayesian confidence level that there is some, and let's not call it God because that's a freighted term. Let's just call it some infinite source of goodness or beautiful power in the universe, right? Simple things can do that. You can increase your credulity in the goodness of life. And we have this bias as humans towards negativity bias, well-known fact. So what I want to do is let's call God good, right? That's where it comes from. God good, same words in German. And when we think about what is good, let's do those things that would devastate us. And a lot of that could be relationships. And there's a powerful concept from network theory, which is that, the number of connections in a network, I'm just saying it for you, it grows as the square of the elements in the matrix, in the number, right? So you think of a matrix with n people, person 1, 2, 3, 4, and then there's 4 other people. There's 16 different pairs, but half of them overlap. The diagonal is where you know each other, yourself. But that still grows as n squared. So those connections increase and decrease, right? Like, you ever have 2 friends that are fighting and like you're kind of upset, even though you're not fighting with either one of them? So like a network grows like that. So you want to increase your network as much as possible, but only the kind of high quality interstices between them. And I think in doing so, you make yourself fragile, not anti-fragile. And I think that is where purpose and maybe approaching some notion of God can come from.
So that is a source of meaning, maximizing the goodness in life. And the way you know it's good is if it's taken away, it would devastate you.
That's one way. Think about it. Your brand, your business, your spouse, your kids. I mean, parents can't count them. I've known parents that have Jim Simons, here's a perfect example. He's one of my oldest friends and mentors. He is one of the richest people on earth. Gulfstream, mega yacht. This is all documented, books about him. He lost 2 sons as adults. And I hear people say, I'm so jealous of Jim Simons. Would you take everything? I don't know where he has that strength, and his wife, Marilyn, and his first wife, Barbara. I'm not like that. Some people there are angels that walk among us. And there's this famous prayer. It's like, God, there's an old saying that like one of the hardest tests there are in life is to be given a lot of money. And you see it like happens with like people that win the lottery or whatever, or NFL football players after their career's over, they're broke, right? And I always like, God, please test me with money. That'd be great. But in reality, you should never say I want what X person has, unless you're willing to take everything. And you'll find you won't want to take everything.
Yeah, I think a lot about the altering effects of fame, of money, of power on people. Mm-hmm. It blinds people, and I wonder about that for myself, because it seems like in themselves these are definitely not the goals. I'm pretty much afraid. I'm not desirous. And I'm definitely afraid of each of those things: money, fame, and power. But it seems the dreams I have as consequences can often have these things. And I'm really afraid of becoming something that would disappoint me when I was younger, that I wouldn't recognize, because change happens gradually.
But are you using yourself as the touchstone, to use the assay amount? Like, what is your rubric to apprise if you have lived up to that 12-year-old, whatever year old Lex? Like, how will you know or not know if you've let yourself down? Or like, I always think, live to impress yourself. Like, I don't care if I have followers. Like, it's nice or whatever, but it's hedonic and it's just never ending because you'll always see the next level. But I think it's pretty damn cool that like I've gotten to go to these places, the South Pole, and I've done these things, and I've made a family, and I'm able to teleport my values into the future through my children, and I've had ideological children that So by what metric, have you not already A, impressed yourself, and B, could you let yourself down? I don't want to turn this into therapy
I
session,
think some of it is psychology. For me, I'm very much just never. I'm highly self-critical. I'm never happy with what I've done, but I'm always happy in the way that you describe, which is that the Vonnegut thing, where you just often during the day, I will feel. I don't know. I just remember just eating beef jerky and being truly happy. That was just last night, and I have that all the time. And that, to me, is why I mean, that feels to me like a healthy way to live life. And at least for me, it's the one I really enjoy. A lot of people tell me that maybe being so self-critical, so hard on yourself is not a good way to go. But more and more as I get older, I realize it's just who I am. You have to a certain point accept this is how I'm always going to be this self-critical.
Yeah. It's like the Oracle of Delphi, right? You know thyself. But I want to leave you with one last thing, which is to say, just on this topic, it could be different, right? We could go down to the ocean and get some krill instead of the 7-Eleven. It could be that we have no other taste buds. And Eric's talked to the 4 dimensions of, the vibration of your tongue, right? It could be like there's one, and it's just like, not Memphis barbecue or whatever you like in your Slim Jim. It could be something. It could be very boring. Similarly, what if that's a clue? What if that's giving us evidence? Here's another clue. There are many animals. Most animals have single monocolor vision. They only see in black and white intensity. They only have rods and no cones. We could be like that, but we're not. Why is that not a clue? If God's not going to hit you over the head and say here I am, because then everybody would believe in him. And there's very simplistic. I've had debates even with famous atheists like Lawrence Krauss, who's self-declared militant atheist. And I was like, well, I don't believe in the same God you don't believe in. Some guy in a white beard in a chair. That's infantile. I gave that away a long time ago. But what if there are clues? What if Yang-Mills theory and Maxwell's equation, those are beautiful. If you've ever seen expressed in tensor notation, Einstein's equations or Maxwell's equations, and then Maxwell's equations riding on Einstein's, it's unbelievably beautiful. Doesn't have to be that way. That we can comprehend it, that's a crack. Maybe that's where the light gets in, and the light is what reveals what's beautiful. So I don't believe in God. I think that's a stupid notion. Do I believe in God? Sometimes I joke, I wonder if God believes in me, more than if I believe in, he needs Brian Keating. It's one of my friends is a rabbi. He's what would I be doing if I were God? Exactly what God's doing right now. You think I know more than God? Give me a break.
Leaving clues of beauty for these hairless apes.
Yeah.
And to see what they do with this, and then marvel at both the tragedy of what those apes do to each other, and the rare moments of when they understand deeply about how the world works. Brian, you're an incredible human being. I'm a big fan, and I'm really honored that you first of all, shower me with rocks from the moon.
From space.
Space
dust.
Space
the
dust. And
crystals, magical crystals, healing crystals.
Yeah.
That you can use for good.
And tell me your story and spend your really valuable time with me today. This was amazing.
That was a great pleasure for me, Lex. Thank you so much.
Thanks for listening to this conversation with Brian Keating. To support this podcast, please check out our sponsors in the description. And now, let me leave you with some words from Galileo Galilei. In questions of science, the authority of 1,000 is not worth the humble reasoning of a single individual. Thank you for listening, and hope to see you next time.